Hi everyone, in this section we will talk about problems involving big integers. So what is a big integer? A big integer is a number that has lots and lots of digits. That means if it has lots of digits, let's say it has greater than 18 digits, okay? So that means you cannot store that number in int because int has a range of 10 per 9, and you cannot store that number in long int. So long int also has a range of 10 per 18. So if you have a number, let's say, which has 200 digits in it, so definitely you do not have anything in C++ to handle that. But in Java and Python, it's quite easy to handle those things because Java provides a class that implements a lot of arithmetic operations on big integers, and in Python it is also very easy to handle big integers. But in C++, if you have a very large number that contains 200 digits, then you have to create an array and you have to define all the operations on the array. For example, if you want to multiply two numbers, maybe you have 1 2 3 4 5 6 7, then you have to simulate those operations on the array, okay? And you have to put a loop to do a digit by digit multiplication and so on. So in this video I will show you one example where we can compute large factorials in C++, and we will see more on big integers using Java in the coming videos, okay? So let's compute large factorials in C++, where you will see how an array can be used to store an big integers, okay? So let's take an example and let's see if you want to compute let's say 100 factorial, okay? So then this is a difficult problem to solve, but with the help of an array we can actually achieve the correct answer. So suppose I create an array like this and it has a capacity to store, let's say, lot of digits, okay? And what I can do, I can start with a value of 1, because if you need to compute, let's say, 5 factorial, so you need to multiply 1, then multiply it with 2, multiply it with 3, 4 and 5. That you already know. So what you need to do, you multiply this array with 2. So you see, okay, 1 into 2 is 2, so you get this inside the array. Then you multiply it with 3, you get another array, or in the same array you make an update, you make it as 6, you multiply it with 4, and this makes us 24. Now 6 into 4 is 24, so what do? You get a result 24. You have now two parts in this, you have this part and you have a carry part. So if you do 24 mod 10, you get the 4, and if you do 24 by 10, you get the 2. So what I will do, I will store this result in the reverse order. So 6 4s are 24. I will first store 4 here, and then I will store 2 here. If you want to read this number, you can read it in the right to left manner. Then you want to multiply it with 5. So let's see how we can multiply 24 it with 5. So let's say we have 5, and we will do multiplication digit by digit. So 5 4s are 20, so we have 2 as a carry, so 5 2s are 10, okay? And 10 plus 2 is 12. Now we have 12. So what we will do, we will first extract this digit, we will put a 2 here, and we will extract the carry, and we will say, okay, carry will go in the next place, so the next place will be like this. So we get these numbers in the array. So you can see this result is 120, okay? So you can read this result in the right to left order, and this result is actually 120. So this is how we can perform multiplication inside an array. You can also multiply it with 6, you can also multiply it with 15 and so on. So let us try to write some code that will help us to compute big integers or multiply big integers, okay? Okay, so in this function I'm going to in this main I have called a function called big factorial that I'm going to define. So let's make a function called big factorial that accepts the value of number for which we want to compute the factorial. And what we will do, we will first define an array where we will store the digits. So let's say new int of 1000, and I'm assuming that this will have at most 1000 digits, okay? So I can just initialize it with all zeros. So I've created an array that can store up to 1000 digits, and initially all of the digits in the array are 0, but I can start with putting value 1 inside a of 0. So I can say a of 0 is 1 because when you start computing your factorial, you can always start with a value of 1. Okay, then you multiply it with 2, you multiply it with 3 and 4 and so on. So this is why I'm starting with a of 0 as 1. Then what I need to do from I equals to 2, let's say int I equals to 2, I less than equals to n, okay, or the number what I have. What I will do, I will multiply my array. Okay, so I will say multiply whatever number I have in the array A with the number I, okay, and the number of digits in the array, okay, that is going to be denoted by n. So I'm going to say I have number of digits in the array as 1. So this is important to perform multiplication. Okay, for example, if your total array has, let's say, 1000 digits, and currently if you have only 3 digits, let's say n equal to 3, so when you do multiplication with some number, let's say you multiply it with 15, so what you do, you say okay, 15 ones are 15 and 1 carry, 15 twos are 30 and 1 31, 3 carry, 15 threes are 45 and 3, that's 48. So you store this number like this in here, okay, and finally in this array you will now have n equal to 4 digits. So basically this n tells you how many digits you have in the array that you need to multiply. Okay, now some of you may think why we cannot check till we get a 0. So that we cannot do because it is possible that after 4 we have a 0 and then we have a 6. So you cannot stop at actually 0. So you need to know how many digits you have in the actual array, until what point you need to perform the multiplication. So this is one function that we will define. So we have an array A that needs to be multiplied with a number I, and that array has n number of digits. So this is what we will define. So once this multiplication is over, you can simply print the result. Okay, so we will come to it, and before that we need to define this function multiply. So we have void multiply, and here we will get the array A, and we will also get the number of digits n, and I'm passing it by reference. You will come to know why we are doing so, and we are getting the number with which we want to multiply our array. Okay, so that's what we are going to do. So let's make a variable called carry that will be needed, and initially this carry is 0. So what I do, for int I equals to 0, I less than n, I plus plus. So if, for example, if n is 3, then we need to iterate over all the positions from 0 to 0 1 2. Okay, so if you have a number like 1 2 3 in the array, and then we need to iterate over 0 1 and 2. So that's this for loop, and every time you will multiply it with the given number. Okay, so when you multiply number with the current digit, so current digit is given by array of I. So int that product will be equal to array of I multiplied by that number plus some previous carry. Okay, so initially this carry is equal to 0, and then you generate the next digit, or you update the current digit that is given as product modulus 10, and you generate the carry for the next position, that is product divided by 10. Okay, and also after that you need to put a loop while carry is not equal to 0. Okay, so what we need to do, we need to say array of n equals to carry modulus 10 and carry equals to carry by 10. So don't worry if you're getting confused, I will just explain you what I'm trying to do here, and this actually makes this function complete. Now we can just dry run what we have done. For example, let's say you have a number 2 to 9 and you want to multiply it with a number 15. Okay, so 2 to 9 is kept inside the array. Okay, and you have n equals to 3. Okay, so you have number equals to 15. So when you do this multiplication, what do you do? 15 into 2. Okay, so this is array of I multiplied by number plus carry. So initially carry is 0, so that's what is there. So you do 15 to the 30, and when you do 30, and you need to extract two things, you have 0 and you have 3. So 0 comes here, that is in a of I. So a of I is 0 now, and for the next position carry is product by 10. So product by 10 is 3. So this carry goes here. Again you do 15 to the 30 and you add the previous carry, that is 3. So this number becomes now 33. So you put 3 here and you make a carry 3 for the next place. Then you do 15 into 9. So 15 nines are 135 and you add a carry here, that is 138. Okay. So what do you do now? You have 8 here and now you have 13 as the carry. Okay, so now you have 13 as the carry. Now it is possible that this carry can have one or more digits. Okay, so this is possible. For example, in this case it has 2 digits. So what we need to do, we need to put these digits inside this part of the array. Okay, so starting from this particular index, so this index is nothing but the nth index. So I say, okay, array of n equals to carry mod 10. So carry mod 10 gives me 3 and carry equals to carry by 10. So I just remove this digit. Okay, so now carry for my next index and I do n plus plus. So this is n equal to n plus 1 and this is my new carry, that is equal to carry by 10. So old carry was 13, now I have a carry 1. So I put a 1 here and the carry for the next position becomes 0 and this loop basically stops. Now if you see the result of multiplication of 2 to 9 with 1 5, you will get this particular answer. Okay, so effectively this number is 922. Okay, and that is multiplied by 15, so you should get 13830. We can also verify this. So let me open up calculator. Okay, so that's 992 or 922 multiplied by 15. Okay, that is 13830. So that's what we were getting here. Okay, so this is perfectly fine and you can see that our multiplication logic looks correct. Okay, so now what we can do, we can finally print the result. Okay, and also we are doing n plus plus, that will increment the value of n by reference, so we do not need to worry about that as well. So what we can do is, for int I equals to n minus 1, I greater than equals to 0, I minus minus, I can say cout array of I, that's it. I can clear out my memory, I can delete the array and I can return from the function. That's it. Okay, so let's include IOStream. And let's try to run our code. So let me give a number as 5. So I get the answer as 120. So if I give 100 as my input, so I get a very large number in the output, that is actually 100 factorial. Okay, so I'm just printing a space between every digit, but you can avoid that as well. Okay, so we can just skip this space and you can see. So this is the answer of 100 factorial, and you can see this cannot be stored inside a integer. So I hope you got an idea how we can perform multiplication on big integers in C++. And but for many problems I will suggest you to go with Python or Java, that because that is going to save time, and these multiplications you do not need to write explicitly in Python. Okay. Hi everyone, so now I'm going to show you how you can work with big numbers in Python. So basically the best thing about Python is it automatically handles huge numbers. Okay, so it does not matter how big the number is, Python is going to automatically convert that number into a big integer, and it's going to handle everything automatically. Okay, so you can just write the big factorial program just like a normal program. Okay, so firstly you need to take input the value of n, and we will try to compute the value of n factorial, and this n can be large number. Okay, so what we can do is we can say, okay, for I in range 1 to n plus 1. So basically this loop will run from the range 1 to n, and what you can do is you can take a variable called answer, and every time your I is updating you can multiply your answer with the value of I. That's it. And here you can just print out the answer. Okay, so this is nothing but a simple program that will compute the value of factorial. For example, if I give n equals to 100, you will see a very large number in the output. So that is nothing but the value of 100 factorial. And also you can just verify for a smaller number as well, so it will work as expected. Okay, so you can see, so this is how easy it is to compute big factorials in Python. You can also define a function called factorial that accepts the value of n, and you can just move this statement here. Okay, and you can say okay, answer is equal to okay, let me just restructure the code. Okay, so we have answer equals to 1, this, and we can say okay, answer equals to factorial of n, or you can simply say print factorial of n. That's also fine. So we can say print factorial of n. Okay, so this is like a function, and here you have to return the value of answer. Okay, so if you want to create a function, you can also do it in Python. And you can see we are getting the same output. So 5 is not a big integer, 100 is not a big integer, but the value of 100 factorial is actually a very large number that we can compute just by writing 3-4 lines of code in Python. Hi everyone, in this example we are going to discuss a big integer class in Java. I will show you a quick demo of this class, and this contains a lot of inbuilt functions that can help you to do arithmetic on big numbers, GCD calculation, base conversion, power calculation, bitwise operators, and also prime generation. Okay, so let us see few examples in this video, and this class is available in Java only, it's not there in C++. Okay, so what you need to do, you first need to import this class, import java.math.biginteger, and then I have created a function called play with big integers, and I have called this function from main. Okay, so all my code will go inside this particular function. So let me show you how you can create two big integers. Okay, so let's say big integer b1, that is equal to new big integer, and here you specify the value of the big integer as a string. So let's say 1 is a big integer, and another big integer I can create as, let's say b2, that this is equal to new big integer, and here you can give some large number. Okay, so let's say this is a very large number, and what you can do is you can add these two large numbers. Okay, so maybe this is, let's say 12. Okay, so what you can do is you can say okay, b1 equals to b1 dot add. Since b1 is an object, it has a function called add, and it accepts another big integer that you can add to it. Okay, so once you have added these two numbers, you can do system dot out dot println, just like cout in C++, and here you give the print out the result. Okay, so let's try to run this code where we are adding two big integers using the big integer class in Java, and you can see this is the output here. You can also do multiplication. You can say okay, instead of doing addition, I can also do b1 equals to b1 dot multiply, and here I can give the number b2. So you can see that this will, sorry, this should be multiply. Okay, so these are some of the arithmetic operations that you can do. Also you can read input from the user. Okay, for that you need to create a scanner object, just like a cin object in C++. So you have a new scanner, and that reads input from system.in. Okay, so let's call this function sc.next. So I can say string s1, that is equal to sc.next. It will read the next string from the input, and here I can just give this string s1. So this input is read from the user. Okay, so I can just read the numbers from the input as well, and I can do multiplications and additions on them as well. Okay, so this is how you work with input. And also you can have some other functions, like if you want to count the number of bits. Okay, so you can do system dot out dot print ln, and here you can say b1 dot bit count. Okay, so bit count function will count the total number of bits. So this is the total bits, or total set bits, I guess. And if you want to see the total number of bits, then it's called as bit length. Okay, so system dot out dot print ln b1 dot total bits. Okay, so that is given by bit length. So let's see. So you can see out of 54 bits, this number has 29 set bits. Okay, also we can find out GCD. Okay, so if you want to convert an integer into big integer, then also what you can do is you can read a number from the user using a function called nextInt. Let's say we will read two numbers. Let's say we have 15 and we have 25. So let's say we have number a, that is equal to sc dot nextInt. Okay, so we can read it using sc dot nextInt. So I can say int a equals to sc dot nextInt. Okay, int b equals to sc dot nextInt. So these numbers are not big integers. I can just do simple arithmetic with them, but what I can do, I can convert them into big integers, and I can also find out their GCD. So let me print a and b, a plus b. Okay, and if you want to find GCD of two big numbers, you can say okay, b3, let's say b3 equals to that's big integer, big integer b3 equals to new big integer, and here you give. Now you cannot convert a into a big integer directly. Okay, so to do that, you have to use a special function called value of. So what do? You say big integer dot value of, and here you give a, and similarly you can do it for b also. So we have created two big integers from a and b, and now we can print their GCD. So how do you print their GCD? So it's very simple. So you can just call b1 dot GCD b dot b. So system dot out dot print ln, and you can say b3 dot GCD with b4. So find the GCD of b3 and b4. So b3 is an object that makes a call on GCD function with b4 as the input. So this should give me 5 as the GCD for this. Okay, uh, so we have error here. Hmm. Okay, I think this is a mistake. So we do not need to do this thing. So big integer dot value of already returns a big integer. So I think we should use it directly. So let's run the code and see. Okay. Yes. So you can see this GCD is 5. And also let me give you one example of base conversion. For example, if you want to convert a number into, let's say, base 2. Okay, so let's see. So I can say big integer b5, that is equal to new big integer Okay, so here we need to give uh, some number. Let's say number is 9, okay, or let's say number is 13, and we want to convert this number into, let's say, base 2. That's the binary representation of this particular number. Okay, so let's see system dot out dot println, and we give b5 here. Okay, and another thing that we need to do is we can, oh, sorry, this is a small mistake. So 13 is not a binary number. Okay, so we actually, this function basically interprets whatever number you give here, it will be interpreted in the binary format. Okay, so we got a exception. That means this is not the right way we are calling this function. So it expects the number in the binary format. Okay, for example, if you give this number, now this number when converted to decimal will be 9. Okay, so if I see what is b5 now, so let's see, this number should be 9. Okay, so that means here you give the number and here you specify the base, and this will give you the absolute value of that particular number. Okay, so that's what it is. Okay, so if you give base 8 here, so this number will be treated as in base 8. Okay, but let me just say it's in base 2. Okay, so it will interpret the number in given base. Okay, so let's go through one more example where we can compute power of a number. Okay, so maybe you want to do something raised to the power something, so that in that case you can use a power function. So you can say system dot out dot println, and we already have read two numbers 15 and 25. We can do raised to the power b3 raised to the power b4. So we can say, okay, we can do b3 dot power, and here we give b4. So that result will be a large number, and you will see that result here. uh, Okay, so big integers cannot be converted into int, right? So what it basically means is that this number cannot be a big integer. Okay, if you're doing something raised to the power something, that power number should be an integer and the output can be a big integer. Okay, so let's make it as 20. Okay, so that will now have a data type of integer because the power function does not expect a big integer, it expects a integer. Okay, so now you can see b3 raised to the power 20 gives us this result. Okay, so I hope some of the functions related to big integer class are now clear, and you can use them in some of the problems that you might find in online judges. Okay, so next example will be on big factorial. Let's see that. Hi guys, so now I'm going to show you how you can compute a big integer in Java. Okay, so what we are going to do, we are going to define a function, static, return type is big integer, and the name of the function is factorial, and you accept an integer and we will return a big integer that corresponds to n factorial. Okay, so what we can do, we can initialize a big integer, that, let's call it as b, and let's say it is initialized with a value of 1. Okay, so that's what you need to do, and after that you need to put a for loop from I equals to 2, I less than equals to, let's say, n, I plus plus, and every time what you need to do, you need to multiply your big integers with a number. Okay, so b equals to b dot multiply, and here you should give a big integer, and that integer can be made from this integer. Okay, so we had discussed one function called value of, and we can use that value of function to convert I into a big integer. Okay, and that's it, and finally we can say return b. So now you can see our function is ready, and in the main we can just call this function, and what we can say, let's say int n equals to 100, and we can just call system dot out dot println, and here we can give fact of n. Okay, so let's try to run this code and see. Okay, now you can see we are getting the same output that we got in C++ and in Python, and this is how you can compute factorial using big integer class in Java. Hi everyone, so now we will discuss this problem from Spotch. It says there are two girls, they have 10 apples together, and it is known that the second girl has 2 apples more than the first girl. Okay, so let's say we know the sum of apples, so let's say y plus x equals to 10, and it is also known as y is 2 more than x, so y equals to x plus 2. So if I substitute the value of y here, so I get x plus 2 equals to 10, and this gives me 2x equals to 8. That gives me the value of x as 4, and that gives me value of y as 6. So very simple question, but now it says instead of giving you this problem statement, you're given these numbers as big integers. Okay, so you're given that two girls have apples and the sum of apples is a big integer. Okay, and also you're given another number, okay, in which you're given that the second girl has two apples more than the first girl, or it is given she has k more apples than the first girl, so you have to find out the value of x and y. So it's a very simple arithmetic problem, but the only thing is you have to work with big integers, since this sum of apples is 10 raised to the power 100, and you won't be able to hold this number in a integer or a long int kind of a thing. Okay, so very simple question. So what I need to do is I know that x plus y is given as, let's say, uh, n, and it's also given that x is 2 more than y. Okay, so if I just compute this term now, it becomes 2 plus y equals to n. So this gives me 2y equals to n minus, so this is actually k. Okay, so 2y equals to n minus k, and if you see, firstly you need to do a subtraction. Okay, so you have to subtract k from n, that what I do here, and then I have to compute y or x, whatever you can say. I have to do a division by 2. So we have to use this function called divide, where we divide with a big integer dot value of 2. So we basically divide this big integer with 2, and this gives us one value, that's y. And if we want to get the next value, that is, let's say, x, that is basically y plus k. So for that I just do dot add k function, and this gives me the values of both y and x. Okay, so in my code I have interchanged the variable names x and y, but this is what I am doing here. So basically it's nothing but just an implementation of big integer functions in Java, or you can easily do it in Python as well. Okay, so that's all what you need to do, and in the main we have written some logic. We have created a scanner to take input, and for each test case we read the values of n and k, and we compute n and k, and that's it. Okay, so this is how easy it is to solve this problem. You can also try this problem in Python, and that would be easy to solve as well. Hi everyone, now we will discuss birthday paradox problem. It says, what is the minimum number of people that should be present in a hall so that there is 50% chance of two people having same birthday? Okay, so let's say in a hall of n people, what should be the value of n, so that if you pick two persons, then there is a chance that these two persons have the same birthday. Okay, so at least two persons have the birthday on the same date. Okay, so you want to find out what is the value of n, the number of people in the hall, and they should have same birthday. Okay, and that probability should be equal to 50%. Okay, or let's say some x percent. So that this number can variable, but in this question it says uh, there should be a 50% chance that the two people have the same birthday. Okay, so let's make this question little easy. Let's see what how many people should be there in the hall if I say the probability is 100%. Okay, so that at least two people have the same birthday, then the probability should be 100%. Obviously, if you want with 100% confidence that at least two people will have the same birthday, then if you have 366 people, okay, and assuming it's a non leap year with 365 days, then you can say at least two people will have the same birthday, and we are almost 100% sure. Okay, and we are almost 100% sure. So that is the case when this probability is 100%, but we cannot figure out directly what should be the answer for 50%. So we need to further break down this problem. We need to break it down into smaller components. Okay, so let's try to assume, suppose we have a single person in the hall. Okay, and let's also say that two people having same birthday is actually a complement of all people having different birthday. Okay, so that means of at least two people having same birthday. So let's say if this probability is p, then the probability of all people having different birthday, okay, that will be 1 minus p. Okay, all people having different birthday. Okay, because if we want to compute any two people having same birthday, that will actually be a little difficult, because you do not know which two people will have same birthday. But you can actually compute the probability of all people having different birthday, and this probability will be, let's say, x, and that x will be equal to 1 minus p. Okay, so let us first try to find out this value of x. What is the probability that all people will have different birthday? So suppose I start with two persons in the hall, and I say, okay, what is the probability that these two people will have different birthday? So the first person, let's say, can select his birthday in 365 C1 ways upon 365. So this will be the probability, that is 1 actually. So if we have just one person in the hall, and I want that this person should not have a birthday that collides with another person, so obviously there is a 100% chance that this person has a different birthday. But suppose you have two persons in the hall, so first person can choose his birthday in 365 ways, second person must choose his birthday in 364 ways. Okay, so that it does not collide with the first person. Okay, so if you just figure this out, it comes out to be 99.73%. That means starting with 100%, if you add one more person in the hall, the probability that these two persons have different birthday falls down to 99.73%. Now let us talk about what will happen if we add one more person in the hall. Okay, in that case, if we want all of them should have different birthday, this probability would be 365 upon 365 multiplied by second person can choose his birthday in 364 ways out of 365 ways, and third person can choose his birthday in 363 ways out of 365 possible options. So this probability comes out to be 99 point I think 17%. Okay, so you can calculate it on your own. So what we can say is, as you keep on adding more and more persons in the hall, okay, the probability is going to dip. Okay, so maybe it becomes 70% at some point, it becomes close to 50% at some point. Okay, so you can see there is a reduction in probability as the value of number of people in the hall increases, and that is also obvious. Okay, so that is also obvious because the more is the number of people in the hall, the more is the chance that two people will have the same birthday. So what we need to do now is, okay, so what we need to do is, we need to keep a value of n. Let's say it starts from 1, it becomes 2, it becomes 3, and so on. And we need to compute the corresponding probability of people having different birthday. Okay, so what is the probability of different birthday at n equal to 1? It's 100%. At n equal to 2, it is 99.73%. At n equal to 3, it is 99.17%. Okay, and you will see when you reach n equal to 23, it becomes actually less than 50%. You will see, you will say this. And what we can say about the probability of having same birthday, okay, so it will be something of this form, 0.27%, it will be of the form 0.73%, and you will see it will be slightly greater than 50%. Okay, so approximately, let's say this is 50% and this is 49 point something. Okay, so I will show you with the example of a code. So what I'm trying to say is, as you try to reduce the probability of having different birthday less than 50%, the probability of having same birthday slightly overshoots 50%, because it is possible, since we are multiplying floating point numbers, it is possible we may not get exact 50%, we may get 50.1% or 50.2%. so we just need to ensure that the probability of two people having same birthday should be at least 50% or higher. That's what we need to ensure, and that means probability of having different birthday should be at least 50% or less. So what we need to do, we can just put a loop in which we are computing this value and we are also computing this value. That's it. Okay, so let's try to see how we can do it. And also we know that if we have n equal to 3, what we need to do is, we can compute this probability as 365 upon 365 into 364 upon 365 into 363 upon 365. Okay, so the number of terms that we will multiply will depend upon the value of n. This is how we compute this probability x. Okay, and also what you need to do, you do not need to multiply all of these terms always. So this result is already computed at this particular point. So this is 99.73 into this term. Okay, so you always generate the next term and you multiply it with the previous result. So this is my previous result. Okay, or the previous probability or previous value of x. Okay, so this is how we can actually solve this problem. So let's quickly write the code. So let's write the code for the birthday paradox problem. So I'm taking a variable float x that is equal to 1, and x denotes the probability of two people having the same birthday. Okay, and the number of people in the hall, I can say, is let's say initially 1 or 0. We can start with 0, and I'm going to take two terms. One is going to be my numerator, that is 365, and I'm going to take a denominator that is also 365. So denominator is going to remain same throughout the implementation, but the numerator is going to decrease, because when we compute the probability, the number of ways in which a person can select his birthday reduces as the number of people are going to increase. So from the user, I will accept what is the probability threshold. Does he want to compute at 50% or 60% or whatever? So we can say, okay, float p, and we can say c in that particular probability. Okay, and here I can say while my probability x is greater than 1 minus p. Okay, so that means this while loop will stop when x is less than the threshold. So if someone says, okay, I want the probability of having same birthday should be at least 60%, that means the probability of having different birthday must be less than 40%. Okay, so let's say p is 60%, and in our example it was 50%. So I can say while x is greater than 40%, so that means this particular loop will stop when x is actually violating this condition. Okay, so x is actually starting from 100. Okay, so x is starting from 100, or let's say 100 upon 100, x is starting from 1.0, and while this x is greater than zero point 0.4. That means loop will stop when you exceed this condition, when when the value of x becomes less than zero point 0.4. That's where the probability of having same birthday shoots 60%. Okay, so that's what I'm saying here. So what I do, let's compute the probability. So probability is x, and x can be computed as x into the previous result into the current result, that is numerator divided by denominator. Okay, and every time we go, we have to reduce the numerator and we have to increase the number of people, that is people plus plus. That's it. And finally, if you print the value of x and the number of people at every step, you will see uh, we will get something that we have seen in the example also. So if I print people and if I print the value of x, that is my probability. Let's see the result. Okay, so let me give input as zero point 0.5, and you can see that this loop goes on and you can see a similar trend in the probabilities getting reducing. Okay, so at this particular point, when you have 23 people in the hall, and that means the probability of having all people having different birthdays 0.4927, that means probability of any two people having same birthday is now greater than 50%. Okay, so this is how we can solve the birthday paradox problem. You can try out with different values of p. Let's say p is 0.7. So if you want two people having same probability with a confidence of same birthday with a confidence of 70%, then the number of people should be 30 in the hall. Okay, so with only 30 people you can say with 70% confidence that these two are going to have same birthday. So one corner case that we need to handle is the case of 1. Okay, so you can see when you are giving 100% confidence, this is not giving the correct answer. So a reason being, so the values become very small and you are not able to store such small numbers in your float. Okay, so that's why this case should be handled separately. So let's handle the corner case also. So you can see if p is 1, then you just do cout 366 and l and return. Okay, something like this you can do, and it should be return 0. Okay, so let's see, if I give 1 as my input, so I get 366 as my answer. So I hope this is clear and you will be able to solve a birthday paradox problem now. Hi everyone. So now in this video, I'm going to throw some light on some interesting use cases, interesting facts about Fibonacci series. So I think you already know what is a Fibonacci series, and you know the nth term of the Fibonacci series is sum of previous two terms. Okay, and the series looks something like this: 0, 1, 1, 2, 3, 5. But it is possible that this series can come in lot of problems and it might not be mentioned that it's a Fibonacci series problem. Okay, so for example, if I will discuss two sample problems. So first problem is, find the number of Boolean strings of length n with no consecutive ones. Okay, for example, let's say you are given n equals to 2 and you want to find out the number of strings of length 2, and they should be Boolean strings in which there is a no consecutive one. Okay, so you can see you can form three strings. Okay, and if I talk about the recurrence here, okay, so if we want to solve this problem recursively, what we can do is we can have two cases. Okay, for example, if I have a string of length n minus 1, and if I think of what I can fill in the last place, so suppose if I fill a 0 here, I can make the number of strings, let's say f of n denotes my final answer, that is the number of strings of length n I can make with no consecutive ones. Okay, so if I see a sub problem of length n minus 1, and if I say okay, I can make number of strings of length n minus 1 as f of n minus 1, and I can put 0 on the last digit. Okay, so that will be one part of the problem. And another part would be, I say okay, no, I want to put 1 in the last digit, and if I put a 1 at last place, what I can do is I cannot have a 1 at this place, I must have a 0 at this place. So if you put a 1 here, so the last two places are fixed, and you are left with a sub problem with n minus 2 length, and you can see your final outcome will be equal to f of n minus 1 plus f of n minus 2. So that again is a Fibonacci recurrence. So again, here it was not mentioned it is a Fibonacci recurrence, so either you make small test cases and then verify that your outcome is actually a Fibonacci recurrence, otherwise you try to build out some recurrence out of the problem. Okay, so another question, find the number of ways to build a wall of size 2 cross n. Okay, so you have a wall of size 2 cross n with bricks of size 1 cross 2 and 2 cross 1. Okay, so that means you can either place the bricks like this, or you can place the bricks like these. Okay, so again, if I just try to break down this problem, I say okay, I will place the first brick in a vertical direction, so I will have a problem which is of length n minus 1. So number of ways to fill this wall will be f of n minus 1 plus, what I can do, I can say no, I will first place the brick like this, so that will occupy 2 units, and we have no option on the top, we have to fill the wall. Okay, so the remaining wall can be filled in f of n minus 2 ways. So again, you can see f of n is nothing but sum of previous two terms. Okay, similarly you can have a problem in which a boy has to climb a ladder, and he can take a jump of 1 or he can take a jump of 2, and you have to find out the number of ways to reach the top. So you can see on the top the boy can either come from this step or he can come from this step, so the total number of ways to reach the nth step would be sum of f of n minus 1 plus f of n minus 2. So you can see there can be plenty of problems which either have Fibonacci sequence or they have Fibonacci like sequence. Okay, so the approach to solve this these problem is, okay, so how do we compute the nth Fibonacci number, that I'm going to discuss. Okay, so you already know there are a lot of ways, so there is a recursion, so this is generally I will not prefer in any problem unless n is very small, let's say n is less than equal to 20, only then you should go with recursion. Okay, and this complexity is 2 raised to the power n. You can use top down dp, that is you can memorize your values, so this complexity would be order of n, and it will also take a space of order of n due to the call stack and the array that you are going to memorize. So bottom up dp is also going to take order of n time because of the uh, array that you are going to memorize. So you can use dp with space optimization, that is basically the 3 variable approach. Very simple, you say okay, my next variable is sum of previous two variables, and then you update your previous two variables. So that's pretty nice approach, and that takes order of n time and it takes order of one space. And another approach that we have discussed in the mathematics section is matrix exponentiation, that can solve this in order of k cube log n time, and in the case of Fibonacci this k is 2, so it's order of log of n, and that's pretty good approach and it's quite fast, and it can work for large values of n such as n is 10 per 18, and you know log of 10 per 18 to the base 2 is just around 60. Okay, so that means this approach is quite fast and you can compute large Fibonacci numbers in almost constant time. Okay, so there is another formula that's called Binet's formula, and it's an approximation to compute Fibonacci. So it does not fits well for large Fibonacci numbers, but it works well up to a certain range, so that range you can figure out. So I will just tell you what is this formula. Maybe sometimes you might see this formula somewhere, so that's why I'm telling you this formula. So it is 5 raised to the power n minus of 5 raised to the power minus n divided by under root of 5. Okay, so you find the nearest integer to this value. So if you want to find out the nth Fibonacci number, you can just use this formula and you can do it in order 1 time. Okay, So for very large values of Fibonacci it does not work, but for smaller values and it works well. Okay, and this also helps you to compute Fibonacci in order 1 time. Okay, so there is one amazing method that is given on Code Forces. It's basically derived from matrix exponentiation. So they have a result which is derived, so I will show you that result. And why you can use that method is because the code is very simple and it can be implemented quickly. Okay, so if you need to implement matrix exponentiation, it will take little time, but what they are doing is they are trying to express nth Fibonacci in terms of f of n by 2th Fibonacci. Okay, so that's some kind of a divide and conquer algorithm they are using, and this actually can be derived using matrix exponentiation also. Okay, so what they have done is they have kind of used the result from the transformation matrix of matrix exponentiation. Okay, so this complexity is also order of log n, but the code is also very short. So if you carefully see, what they are doing is they have a formula where they are expressing f of n in terms of f of k, and you can see what is k is nothing but n by 2. Okay, so k is n by 2, so it says f of n by 2 into f of n by 2 plus f of n by 2 minus 1 into f of n by 2 minus 1. Okay, so this is the formula when n is odd. Okay, so this is the formula when n is actually even, and when the n value of n is odd, they are saying okay, f of n is nothing but f of n by 2 into f of n by 2 plus 1 plus f of n by 2 minus 1 into f of n by 2. Okay, and they are taking a mod at every step so that in order to avoid overflow. And you can see what is f. So here, since the value of n is very large, we cannot maintain a dp array, so they are using a hash map. And also another advantage of using a hash map is that if you are, let's say, computing 10 per 18 and you are doing n by 2 kind of a thing, then only few of the cells, okay, in the array will be used. And since you cannot make a very large array of size 10 per 18 and only some of the cells will be used because of this property, f of n depends upon f of n by 2, it depends upon n by 4, and so on. So it's better to make use of a hash map because it will store only these values. Okay, so you will make limited number of calls, and the overall complexity is given as log n into log of log n. So I'm not diving into the proof of this, but you can read this article on Code Forces, and this is the exact recurrence that is given to you. Okay, so this is one way that might be useful in some of the contests where you have to compute large Fibonacci. Okay, so either you can go with matrix exponentiation, but if you want to save time, you can just implement this recurrence where we are just expressing nth Fibonacci number in terms of f of n by 2th Fibonacci. Okay, and this is the code. Okay, so very simple. It's a bottom up dp only. Okay, so it's a bottom up dp. We are checking if a value is present, then we return that value from the hash map. If it is not, then we compute it. Okay, so that we do not rework on the overlapping sub problems again and again. Okay, so you can just bookmark the link. So we have discussed all possible ways to compute the nth Fibonacci, and most of all of your problems in which you need to compute Fibonacci can be solved by one or more ways that I have discussed. Okay, so there are some interesting properties and theorems that are also related with Fibonacci sequence. So there is a theorem. It says each positive number can be written in a unique way as a sum of one or more Fibonacci numbers such that sum does not include any two consecutive Fibonacci numbers. Okay, so you can see any number can be expressed as sum of other Fibonacci numbers, so that is quite possible. And these any two numbers are not consecutive. So you may get a question, okay, given a number, is it possible to express this in this particular form? So you can say yes, it is possible because it's of this theorem. And that okay, so that's one thing that you should know. It may or may not be that useful. Okay, and also there is another theorem which says last 1 2 3 and 4 digits of the Fibonacci repeat with a period of 60, 315 and 15,000. Okay, so after every 60 numbers, the last digit of the Fibonacci will repeat. Okay, after every 300 numbers, the last two digits of the Fibonacci, nth Fibonacci will repeat after every 300 Fibonacci numbers, and so on. Okay, and similarly for last three digits, and similarly for last four digits. So this is another theorem that may or may not be useful. So these were the some interesting facts about Fibonacci series, and that's it, and we will discuss another series in the next video. Hi everyone. So in this video we will talk about another interesting series, that is the binomial coefficient, and that is widely used in a lot of combinatorics problems. So as you know, binomial coefficient is denoted as NCK, where this also denotes the number of ways to select k objects uh, out of n possible objects. Okay, number of ways to select k items out of n possible items. Okay, so this can be used in some of the problems. I will discuss one sample problem out of n possible items. Okay, and this value is also written as uh, n factorial divided by n minus k factorial into k factorial. Okay, so this is the way to compute this particular value, and it can be difficult if the value of n and k are large. Okay, and there are some tricks that you can use in some of the problems. So one such trick is that you can use this property nck is same as ncn minus k. Okay, so that means maybe if you're doing something of this form, let's say 10c8. Okay, so then you can simply compute 10c2 uh, because of the symmetricity in the binomial coefficient. Okay, so for example, if you see the coefficients in this series x plus y cube, so then these coefficients are this is written like this: 1 plus x cube plus 3x square y plus 3xy square plus 1y square. Okay, so if you just have look at these coefficients, okay, so that's 3c0, 3c1, 3c2 and 3c3. So you can see, if you read it from right to left or left to right, that is basically same. Okay, so that's one property that you can use, and obviously computing this is easier than computing this value, and although this will give you the same result. Okay, so that's one property that you can use in some of the problems. Okay, let's discuss some more properties. So if you want to compute a lot of values of nck for different values of n and k, then we can use bottom up dp. Okay, and we can also use Pascal's triangle in some cases. Okay, so let's see what is bottom up dp. Okay, so firstly we need to know the base case. So c of n comma 0 is same as c of n comma n, and that is equal to 1. And there is a property, there is a formula in which we can say nck is equal to n minus 1 ck minus 1 plus n minus 1 ck. Okay, so you can see, if you want to compute nck, it can be expressed as a sum of two sub problems. Okay, so I will also explain you with the help of a table. So let's build Pascal's table. So we have 1, we have 1 comma 1, and we have 1 to 1. Okay, now you can see, let's denote this as n, and let's denote this as k. So what you need to do, suppose you want to generate the binomial coefficients for the next row. So what you do is you first place one here and you place another one here, and then for all other terms you can say, okay, this is nothing but 1 plus 2, that is 3, and this is nothing but 2 plus 1, this term is also 3. So if you want to compute the coefficients for the next row, you put 1 here and you put 1 here. So this is nothing but 1 plus 3, that is 4, and this is 3 plus 3, that is 6, this is 3 plus 1, 4. So this is how you can compute the binomial coefficients for the next row by combining the results from previous row. Let's say this index is nth row and the kth column. So what you are doing, you are adding these two terms to get this value. So clearly you can verify this formula that nck can be written as sum of previous row, that's n minus 1, n minus 1 ck. So basically this term and this term plus this particular term. So this particular term is nothing but n minus 1 ck minus 1. Okay, so this is another formula that can be used. So either you can call it as Pascal's triangle or you can call it as bottom up dp. So both are exactly same in this case. Okay, and this is how you can build up a table of binomial coefficients that may be useful sometimes in some of the problems. Okay, so now let us discuss one problem where we can use binomial coefficients. For example, you are given a 2-day grid, okay, and you are interested in finding out the number of ways to reach towards the bottom of the grid. Okay, so suppose it's given that you can take only right moves and you can only take down moves. So you want to find out what is the total number of ways starting from this point to reach this point. Okay, so obviously what we can do is we can take one jump, we can end here, we can take another jump, we can take another jump. So we can see if you have four number of columns, you require actually three jumps to cross all the columns. Similarly, if you have one, two, three, let's say five number of rows, you will require four number of jumps to reach the last row. Okay, so one possible way could be you go towards right and then you go towards down. Another possible way could be you go towards down and then you go towards right, or it could be you go right, you go down, you go right, you go down, you go right, you go down. So clearly if we try to arrange all possible ways, so it will be, we have m minus 1 moves that can go right, we have n minus 1 moves that can go down. Okay, let's say we have n cross m matrix with n rows and m columns. So we can have n minus 1 moves for down and we can have m minus 1 moves towards right. So if I arrange these moves in any particular order, okay, then uh, then I will definitely get away. Okay, for example, if I do right, 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 followed by down, down, down. So this is a valid way. So basically I'm saying, okay, just place all of these moves in a single line. You say right, 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 and then you say down, down, down. You find all the permutations of these moves. Okay, so you find all the permutations of these moves. So maybe you go right, then you go down, then you go right, and then you go down, down, and then you go right. So basically the number of right and down moves should remain same. So basically we have to move m minus 1 times right and minus 1 times down. So the total number of ways will be the total number of ways to permute all these moves. Okay, so we can permute these in m minus 1 plus n minus 1 factorial upon, we have to divide by number of identical moves. So that is m minus 1 factorial and n minus 1 factorial. So that is equal to uh, m plus n minus 2 factorial divided by m minus 1 factorial and n minus 1 factorial. Okay, so this is not exactly a binomial coefficient problem, but you are it's a PNC problem, you can say. Okay, so it might be possible that you need to compute these factorials, and it is also possible that you may use some bottom-up DP method to compute these values. Okay, so that's all for this video, and thanks a lot. Hi everyone, in this video we will discuss another important series that is called as Catalan series. Okay, so this is a series that is quite popular and it can come in lot of combinatorics problems, and especially those questions where you have some kind of pattern that is recursive. Okay, so you have a recursive structure in the problem. You will find that this series can fit actually really well. Okay, so I will give you one example and where this series is used. For example, if you want to count the number of binary search trees, okay, with n nodes, and those nodes are numbered from n. Okay, so let's see how many bsts you can have with n number of nodes. Okay, so let's say n is 3, so you can have these kind of bsts. So you can have 1 followed by 2 followed by 3, or you can have 1 2 3, or you can have 1 followed by 3 followed by 2, or you can have 3 followed by 2 followed by 1, or you can have 3 followed by 1 followed by 2. Okay, so you can see you can make five structures for value of n, that is 3. Okay, and you can also verify the third term of the Catalan series is 5. So basically the answer of this problem is nothing but the nth Catalan number. Okay, now you, you might ask, how do we compute nth Catalan number? Okay, so there are two ways to compute it. One is a direct formula. Okay, and there is also a recursive relation that we can build. Okay, so another is your recursive relation. So first I will tell you the direct formula. So if you want to compute the nth term of the Catalan series, you can say the nth term is given by 2n upon n plus 1. Okay, so if you put the value of n as 3, it becomes 6c3 upon 4. So this is equal to 6 into 5 into 4 upon 1 2 3 and 4. So this goes off and this goes off, so you can see you are getting an answer that is 5. So that means the third term of this particular series is 5, and that also represents the number of bsts that we can make using n nodes. Second is recursive relations. Okay, so let's try to derive this recursive relation quickly by using this bst example. Okay, so let's say in a bst you can have any node as a root node. Okay, so if you're given nodes from 1 to n, okay, and let's say we want to make ith node as the root node, then what can happen in that case? So if you put ith node as the root node, okay, then you can put all these nodes in the left part of this tree. So the left part of the tree can contain I minus 1 nodes. Okay, and what about the right part of the tree? So right part of the right part of the tree will contain n minus I nodes. Okay, and how many bsts you can make using I minus 1 nodes? Okay, so let's say f of n denotes the number of bsts that we can make by using n number of nodes. Okay, so if we have a smaller tree in which we have I minus 1 nodes, let's say the number of subtrees is x, and that number of subtrees is f of I minus 1. And similarly for the right hand side part, we can say the number of possible bsts that we can make in this right subtree is y, and that is equal to f of n minus I. Okay, and if you want to calculate the total number of bsts for this value of I, okay, so that will be nothing but out of x ways you can put any one subtree in the left part, so that is xc1 multiplied by, and you will pick any one possible subtree from the right hand side part, so that will be multiplied by yc1. So this is nothing but x into y, so that is nothing but f of I minus 1 into f of n minus I. Okay, and this you will iterate over all i's. Okay, so you will do a summation over all possible nodes. Okay, so you can put 1 as a root node, you can put 2 as a root node, you can put 3 as a root node, you can put all possible nodes in the range 1 to n as the root node. So you can just say this is nothing but summation over 1 to n. When I put ith node as the root node, the number of trees I get is f of I minus 1 into f of n minus I. Okay, so this is a recursive formula that defines the nth Catalan number, and from here, if you solve this recursive relation using dynamic programming, because there are overlapping subproblems here, you will see it will give you the same result as the direct formula. Okay, so you should know how to derive this relation as well. Okay, now why I'm teaching you this concept is because this problem has been asked in many interviews as well, and sometimes it is possible that it's not directly known that the series is a Catalan series. Then in that case, what you need to do is you try to compute the first few terms of um, first few answers of the problem. Okay, so try to compute first few answers, and if you see if it follows a pattern like this, then you can be sure that it can be a Catalan number. Okay, so it will have a recursive structure in the problem. For example, in BST you have a recursive structure. Okay, so you try to compute the answers for the first, let's say, 3 or 4 terms, and if you see those answers are of this form 1 2 5 14, then you can say, okay, this could be a Catalan number problem. And there are few more applications that are given on Wikipedia, so I will suggest you to go through these applications. For example, the number of ways in which you can arrange Bell parentheses. Okay, so let's say you're given n equals to 3 pairs, and you are asked, okay, in how many ways you can make balanced parentheses or balanced expressions, then that answer is given by Catalan number. Okay, similarly, binary search tree we have already seen, and there can be question in which you might be asked, okay, count the number of binary trees instead of BSTs. You have to count the number of binary trees. So we have already seen, if we generate a BST, the ordering of the numbers is fixed, but we get different structures. Okay, so this is what Catalan of 3 gives us. So we have 5 different structures, and for each structure there is only one way to put the numbers. But if I talk about binary tree, in each structure you can permute the labels of the nodes in any order. So that means for every structure, now I can have 3 factorial binary trees for each structure. So that means if I just want to count the number of binary trees with n nodes, so that will be nothing but that will be n factorial multiplied by my Catalan number. So it will be 2n cn upon n plus 1. Okay, so if you want to count the number of binary trees with 3 nodes, it will be, so this value will be 5 and 3 factorial will be 6. So you will get 30 possible binary trees with 3 nodes. Okay, that you can verify, because these nodes can be permuted in any order. So it can be 3 1 2. Okay, it can be 1 3 2 and so on. Okay, so all of them can be binary trees. Okay, so that's another application. So there are a lot of other applications given. I suggest you go through them, and most of them have this answer as Catalan number. For example, Cn is also the number of ways to form mountain ranges with n upstrokes and n downstrokes, and all of them stay above a horizontal line. Okay, so using these characters, you want to build mountain ranges. So that again is kind of a recursive structure. Okay, you will see in this problem, and you can see for n equal to 3 we have 5 different mountain ranges. So you just need to compute the Catalan number in this problem as well. Okay, so we may not discuss the proofs for everything, but I will suggest you go through the applications once, and that will be really helpful. Okay, so there are, I think, 10 or 12 applications that are given here, so just go through them. And we have already discussed the formula for the nth Catalan number is given like this, so 1 by n plus 1 into 2n cn. And we have also discussed the recurrence. Okay, and this is another application, the number of paths from bottom of the grid to the top of grid that do not cross the diagonal. I think this is also given by the Catalan number. Okay. Okay. So that's it for the Catalan series. And if you want to go into the more details of the implementation, I have covered this in the dynamic programming section where I have explained it in more detail, and I have also covered the implementation, the recursive implementation using dynamic programming. Okay, so that's all for this video. Thank you. Hi everyone. So now I'm not going to discuss any problem, but I'm going to discuss a small hack that might be useful in some of the online contests that you take part. So this is a website called OISIS, that stands for Online Encyclopedia of Integer Sequences, and it's a very powerful website because it helps you to enter a sequence word or some terms of that particular sequence, and you will get to know what this sequence is, where it is used, and what are the other terms of this sequence, or what is the nth term of this particular sequence. Okay, for example, you are solving a problem where you encounter that, okay, for n equal to 2, you make small test cases, and for n equal to 2 you get 2, for n equal to 3 you get 3, and for n equal to, let's say, 4, you get answer as 6, and you're not able to figure out what is the formula or what sequence it is. You can just give those few terms here, and you can try to search for that particular sequence, and it will give you all possible sequences where this series is getting followed. Okay, so it says this sequence basically represents the number of trees with n unlabeled nodes. Okay, so, and you can see you're also given the other terms of this sequence, and maybe you can try out with other sequences as well. Maybe let's give some random terms. Maybe let me give 2 7 11. Okay, and let's try to search it. So now we do not know what sequence is this, but it says it's a sequence in which we have prime numbers, and also there are other explanations as well. So we have a sequence in which prime factor is less than other prime factor of the nth semi prime, so that might not be that useful. This is a sequence called ODS primes, so primes with only odd number of ones in the binary representation. Okay, or you can say these are yes, so these are the prime numbers with which have odd number of ones in their binary representation, and you can see this is the sequence. Okay, so you can actually find out about different sequences from this website, and it may be useful in some of the problems involving sequences. Okay, so that was it. Hi everyone, so in this video we are going to discuss how we can solve some of the counting problems using inclusion exclusion principle. Okay, so you might get some problems in which you have to count the number of objects in a particular kind of a set, and you may be given different sets. For example, let's say you have a set of objects that lie in set A, and maybe there are set of objects which lie in set B, and it is possible that these two sets may be disjoint, maybe not. Okay, they may have some intersection in between them also. So maybe you are asked, okay, what is the total number of objects that are present in set A? Okay, or what is the total number of objects that lie in this region A intersection B? So a very simple formula that you already know is, if you want to find out union of two sets, okay, so that's A union B, that's given as the number of elements in set A plus the number of elements in set B, that's also called as cardinality of the set. Okay, minus the number of elements which are common in both. So this is basic set theory and the set notation. You can also extend it for different number of uh, sets also. Okay, you can have three sets as well. So let us discuss a very simple problem. It says how many integers or how many numbers are there in the range 1 to 100. Okay, how many numbers from 1 to 100 are multiples of 2 or 3. Okay, So how many numbers you have in the range which are multiples of 2 or 3? So what you can do to solve this problem? So firstly, you can say, okay, let A denote be the set of integers in which we have multiples of 2. Okay, so if you want to find out the multiples of 2, then you can clearly say, okay, you can compute 100 by 2 and you find the lower bound of this, okay, or the floor value of this. So obviously we have 50 numbers. How many numbers you have which are multiples of 3? So that's nothing but that's going to be 100 by 3, and that number is going to be 33. Okay, and you, if you want to compute this particular set, okay, so you want to calculate the number of elements in the set A union B, then there will be some numbers which are multiple of both 2 and 3. So that means if a number is a multiple of 2 and it's a multiple of 3, it means it is a multiple of 6. So 6 we have done by doing 2 into 3. So let's compute this set where we are finding the A intersection B. Okay, so for that we need to find out the multiples of 6. So that's going to be 100 by 6, and this is equal to 16. Okay, because 16 into 6 is 96, and if you take the floor value it comes out to be 16. Now if you want to find out A union B, that's going to be nothing but the number of multiples of 2, that is 50, plus the number of multiples of B, that's 33, minus the multiples which have been counted twice. So if you solve this, this comes out to be 67. Okay, so this is how we can actually solve this problem, and in other problems that we will discuss in the next video, you will face with multiple sets. Okay, you can have multiple sets. For example, you may need to find out uh, A union B union C. So that can be written as uh, cardinality of set A plus B plus C minus those regions where you are combining two sets. Okay, so there is a general trend you will see. So whenever you are combining two terms, they will be prefixed with a minus sign. Okay, so minus B union C minus C union A, plus you will combine three terms. So whenever you're combining odd number of terms, so that will be prefixed with the sign of plus. Okay, so you will see this generalized inclusion exclusion principle formula. So what we do is, suppose you have four elements in the set, okay, A, B, C and D. So you have four sets and you want to compute A union B union C union D. So all the terms where you are adding a single set, so those will be added. Okay, all the terms where you are combining even number of sets, for example you are combining two sets A intersection B, those will be subtracted. Okay, and so on. All the terms where you are combining odd number of sets, for example you are combining four sets or three sets, so those will be added. Okay, so basically it depends upon the number of terms you are combining. So if the number of terms you are combining is odd, you will have a plus sign. If the number of terms you are combining is even, you will have a minus sign. Okay, for example like this. Okay, so this is what inclusion exclusion principle is, and we will discuss one interesting problem along with the implementation in the next video. All right. So let us talk about inclusion exclusion principle, right? So this is bit mathematical, but you have also studied this in school while studying set theory, right? So suppose you have two sets, one set is A and another set is B, and let's say these sets are disjoint sets, and you want to compute A union B, right? So let's say A is those people who like apple, B is the number of people who like mango, so they form a different set. And if I compute A union B, right, then it is given by A plus B, right, where this notation represents the cardinality of the set, right, the number of elements in that set, right. So if there are 10 people in set A who like mango and there are 20 people in set B who like apple, then the number of people who like apple or mango is going to be 20, right. So let us make it slightly difficult. Let's say there are people who also like both apple and mango, right? So which means there is some overlapping between the sets A and B, right? So in that case, the formula that we are going to use is, if I want to compute A union B, right, and the cardinality of this set, right, so it is going to be cardinality of A plus the cardinality of B minus what is common, right, because we are counting this part which is common twice, right? So we just subtract this part because it has been counted twice, right? So this is A intersection B, right? So this is what the inclusion exclusion principle is all about, right? So this formula we have written is for two elements, but you can also have this formula has been written for two sets, but there can be more sets. So let us say you have three number of sets. One set is A, one set is B, and one set is C, and you want to find out the union of all these sets, right? So A union B union C, it can be written as A plus B plus C minus A intersection B minus B intersection C minus C intersection A plus this part, which is A intersection B intersection C. Alright, so this is written when we have three sets, but you can also have more number of sets, right? The reason why I'm doing this is because this concept is going to be used in competitive programming, right? So you should understand this very carefully. Similarly, you can have problems in which you need to combine more number of sets, right? So let's say you want to find out A union B union C union D, right? Then the formula would look something like this: A plus B plus C plus D minus, you are going to combine sets in pairs of two, so A intersection B, B intersection C, C intersection D, and so on, right? So this goes on, and then you're going to add let's say you're going to combine sets in triplets, right? Then you will add all those terms in which three sets are occurring. So you will add A intersection B intersection C plus A intersection B intersection D, right, and so on. And then you are going to subtract all those terms in which the set is occurring four times. The number of sets they are occurring are four, right? So if you observe this general trend, right, so what is the general trend? The trend is like this: if you are combining only odd number of terms, odd number of sets, then the sign would be positive. If you are combining even number of terms, like in this case, the sign would be negative. If you are again combining three sets, then the sign would be positive. You are combining four sets, the sign would be negative, right? So effectively what you need to do, you need to generate all subsets. Generate all subsets of this set, and if a subset has odd number of elements, you're going to add the answer for that, and if a subset is going to have even number of elements, you're going to subtract the answer for that, right? Okay, so let's have a look at a problem, right? So the problem is like this: you want to find out how many numbers are there which are less than 1000, right? How many numbers are there such that they are less than 1000 and they are divisible by 2, 3 and 5, right? So how many numbers less than 1000 are there such that they are divisible by 2, 3 and 5, right? So this is the problem I want to solve. So let us see how we can approach this problem, and we are going to use the principle we have learned, right? So first of all, I need to find out how many numbers are there which are less than 1000 and they are divisible by 2, right? So effectively I want to find out the numbers in the range 1 to 999 such that they are divisible by 2, right? So let us find the number of numbers in which are divisible by 2, right? So this would be given by 999 divided by 2, and you take a lower bound, right? So this comes out to be 449 numbers, right? So similarly I need to find out the number of numbers which are divisible by 3. So if you want to find, if you have a number n and you want to find the number of numbers which are divisible by m below n, right? So it is given by floor of this value. You can clearly verify, right? If you have n equals to 1000 and you want to find out how many numbers are divisible by 2, right? So it is going to be this is going to be 499, right? Yeah, and so this is going to be 500, right? Okay, so the number of numbers which are divisible by 3, it would be given by floor of 999 divided by 3, which is equal to 333, right? And I also need to find out those numbers which are divisible by 5, so it is going to be floor of 999 divided by 5. So this comes out to be 199, right? Okay, so now what is the problem statement? The problem says I want to find out all those numbers which are divisible by 2 or 3 or 5. So this is effectively what I need to find out, right? So this can be written as the cardinality of set 2 plus the cardinality of 3 plus cardinality of 5 minus cardinality of 2 intersection 3 minus 2 intersection 5 minus 3 intersection 5 plus all those numbers which are divisible by all three of them, right? So effectively this is what we need to figure out, right? So these terms you already know how many numbers are divisible by 2, 3 and 5. So this basically means all those numbers which are divisible by both 2 and 3, right? So let us find out all those numbers which are divisible by 2 and 3. So this would be given by 999 divided by 2 and divided by 3. Basically I want to find out all those numbers which are multiples of 6, right? So this is what it is going to be, right? So 2 into 3, which is 6, and this comes out to be around 166, right? And similarly you need to find out all those numbers which are divisible by 2 and 5. So you can do floor of 999 divided by 2 into 5, all multiples of 10. So it is going to be 99. And similarly you need to find out 3 and 5. It is going to be 999 divided by 15, 3 into 5. So this comes out to be around 33. Oh sorry, this comes out to be around 66, right? And finally you need to find out all those numbers which are divisible by 2, 3 and 5 all, right? So it would be given by 999 divided by 2, 3 and 5. So 15 into 2, 30, and 999 divided by 30 is equal to 33, right? So now you can clearly figure out what it is going to be. So let us add all these terms. So this term is 499 plus 333 plus 199 minus 166 minus 99 minus 66, and this term is 33, right? So it comes out to be 733, right? So there are 733 integers up to 1000 which have at least 2, 3 or 5 as the divisor, and this also includes 2, 3 and 5, right? So they have either 2, 3 or 5 as the divisor, right? So these many numbers are there, right? Okay, so now I will talk about how to implement the same thing, right? So if you have a array of, let's say, numbers for which you want to find out how many numbers are there for some value less than n which are divisible by these number, right? So first thing is you need to generate all subsets, right? So all subsets of 2, 3, 5 are 2, 3, 5, 2 and 3, 3 and 5 and 2, 3, 5, right? So we need to generate all the subsets, and then we will see if the subset contains even elements or odd elements. If the elements are even, right, then we are going to take their product and divide our n with that, and if the number of elements are even, we will subtract that value, right, that we have already seen, right? Like here, right? So if the number of elements are even, we are going to subtract that value, and if the number of elements are odd, then we are going to add that value, right? And how do you compute subsets? So for computing subsets, I'm going to use bit masking, right? So I will talk about how to use bit masking. For example, if you have a set of elements A, B and C, right? So this is clearly going to have 2 raised to the power 3 subsets, right? Okay, but I just need all those subsets which have at least one element. So I will start, I will just number from 1 to 2 raised to the power n minus 1. So it is basically 7, right? And I'm going to write their binary. So 1 is like this, 2 is like this, 3 is like this, and you have 4, you have 5, you have 6, and you have 7, right? So if you clearly see, right, and if you take a particular number from here and corresponding character from here, and if you choose numbers according to the set bit, right? For example, if you have a 1 here, then if you will choose C from here, right? So you will get C as a subset. You have 1 here, you will choose B, you will get B. You have 1 here, you will get B and C. You have 1, you will get A. From here you will get AC, and here from here you will get AB, and from here you will get ABC, right? So this is what all subsets are going to do, right? So similarly, for computing these numbers, I'm going to use bit masking. So I will basically iterate over range from 1 to 2 raised to the power n minus 1. Then I'm going to generate this number, and then I'm going to extract bits and take that number, right? So what I need to do, I need to take a product of these numbers, right? So that I can compute n divided by the product, okay? And then I will see if the number of terms in it are odd or even. So if the number of terms are, like in this case, are odd, so this n divided by product of the numbers ABC, this will be added to my answer, right? If the number of terms are even, then this would be subtracted from my answer, right? So this is what I am going to do in this. If you need to implement this kind of a thing, right? And all these numbers should be prime, right? And now let us go through the problem. Okay, so the problem is on Coding Blocks Online, and it is also on Hacker Blocks, right? So let us see what the question is saying, right? So it says, after the release of Avengers, Iron Man and Thor got into fight, and Iron Man challenged Thor to find out number of numbers between 1 to n, right? So we need to find out the number of numbers between 1 to n which are divisible by any of the prime numbers less than 20. So this is what we need to find out, right? So we need to write some code which will find out total number of numbers between 1 to n which are divisible by any of the prime numbers less than equal to 20, right? So this is what we are going to see. And in the input, you will be given the number of test cases t followed by t lines, one for each number n for each test case, right? So there are 5 test cases, and you need to find out the number of numbers which are less than 5 and which are divisible by prime numbers, right? Okay, so the only difference you will feel in this problem is that instead of just finding the numbers which are divisible by 2, 3 or 5, you need to find out all such numbers which are divisible by all primes less than 20, right? So we will compute what all primes are there, and now let us implement the same thing, right? Because logic is same, the logic will remain same. Instead of taking 2, 3 and 5, you will take all prime numbers up to 20. So last prime number is going to be 19, right? So given an array of primes, you need to find out what all numbers are there which are less than n and which are divisible by these prime numbers, right? How many numbers are there, right, which are less than equal to n and are divisible by these numbers, right? So this is what you need to compute. Okay, so guys, I'm going to start with the coding part, and let's see, right? Okay, so let us start building our program, and I'm going to use long int because when you are taking product of numbers it can become large, and so I'm taking everything in a long, right? So first of all we need to accept what all test cases are there, and then we also need to create a list of primes. So list of primes which are less than 20. So 2, 3, 5, 7, 11, 13 is there, 17 is there, and 19 is there, right? The next thing is for every test case, right? For every test case I need to input what is the value of n. So let us define n and accept the n. And next thing is we need to create subsets, right? So one thing I'm going to define is up to what value I'm going to iterate, right? So you have 8 primes here, right? So number of primes you are going to have. So total number of subsets you are going to have would be 2 raised to the power 8, right? So total number of subsets are going to be 1 left shift 8. All right, and then because if you have n equals to 3, right? If you have if you had 3 numbers, we saw the total number of subsets are going from 1 to 7, and the total number of subsets are 2 raised to the power n minus 1, right? So these many subsets are there and we are skipping 0, right? So I should also have a minus 1 here, right? Okay, so these many subsets I am going to have, and then I'm going to iterate over all the subsets. Okay, L equals to 1, I equals to 1, I less than equal to subsets, I plus plus. Okay, so what I'm doing here is I'm just going through these numbers, right? I'm going from these number, right? And if you write 1 left shift n, so it is same as 2 raised to the power n, right? So this is what I am doing here, and what I need to compute this product, right? I need to compute this product. So here I do not have any ABC, I have these numbers, these prime numbers 2, 3 and 5, right? So let's say this would be used in the denominator. So let us make one variable denominator which will be multiplied by these numbers, right? Okay, so let us say we have a variable denominator which is going to be equal to 1 LL, means long, and one more thing is I need to find out how many set bits are there, right? Because I need to see if that result that would be added to my result or that would be subtracted from my result, right? So what I'm going to do, I'm going to count set bits. So number of set bits, yeah, how many set bits you have, this is going to be equal to built-in pop count. So guys, this is a very useful method. It is an inbuilt method. It gives you, given a number I, how many set bits it has, right? And then I'm going to iterate over all the bits of that number, right? For some j equals to 0, j less than equal to 7, j plus plus, right? So why I'm doing is you can see, right? If you have 3 numbers, like in this case, right? In this case you had only 3 numbers, but in my case I had 8 numbers. So I need to iterate over all the bit positions starting from 0 to 7. So I'm going to have 7 bit positions, right? And I'm going to see what bit is at a given position, and how do I check which bit is there. For example, if you have a number like this and I want to see what is the bit at this position, right? So what I will do, I will create one mask which looks something like this, 1 left shift 1, right? If you do 1 left shift 1, it is going to become 1 and 0, and if you do an AND, you will get a non-zero value, right? If this bit is 0, then you are going to get a 0 value, right? So if you get a non-zero result by doing number and mask, where mask is 1 left shift P, right? Where P is the position you are talking about, right? So in my case, J denotes the position. So what I'm going to do, if I is my number, and I do one left shift j, sorry, it would be a bitwise AND, right? So which means the corresponding bit is set. So you can say we are talking about the ith row here, and we are talking about the jth bit. Okay, so if this bit is set, I'm going to pick that prime number and multiply it with the denominator, right? So that I can make this product of ABC, AB, AC, BC, and so on, right? So denominator is going to be denominator into primes of j. Okay, and then what I'm going to do, I'm going to see if number of set bits is odd. So and one basically tells me if the result is odd or even, then I'm going to subtract and divided by denominator. Oh, I'm going to add and divided by denominator to my answer, else I'm going to subtract, which means number of set bits is even. All right, and few more things which we need to do here is we need to define what is the answer in the beginning. So let us say LL answer equals to 0, and number of subsets we have already defined. Anything else we are left with? I think that should be good. So let us try to print the answer, right? So cout answer endl and return 0. All right, so let us get the test cases and check, right? So we are getting 4, 9, 11, 14 and 148. Okay, 4, 9, 11, 14 and 17. So minor mistake in the code. Okay, 183 was not there, right? So I think input is wrong. So last input was 18, I guess. Yeah, 18 it was, right? So input is, so output is 4, 9, 11, 14 and 17, which matches our with the output. So now let us try to submit our code, and if you have any confusion, I will just go through it once more and let us see, right? So yeah, we got a correct answer, and so this is how we have solved this problem. And now if you have any confusion, I will just go through the code once more so that you guys are able to uh, clear your doubts, right? So guys, what we did is we iterated over everything, right? We first figured out how many subsets of 8 numbers can be there, right? So we have 8 prime numbers, so we can make how many subsets? 2 raised to the power 8 minus 1 subsets, because we are not talking about the null subset, right? So this is what the number of subsets are, right? And then I started iterating over all the subsets starting from 1 to 2 raised to the power 8 minus 1, and for every number I have a corresponding number in binary which is going to have at most 8 set bits, right? So I iterate over what all 8 set bits are, and here I have a list of primes, right? So I have a list of primes starting from 2, 3, 5 up to 19, right? So 19 is my 8th prime, right? Then I see if this bit is 1, which means I'm just going to take 19 and I'm going to multiply my denominator with 19. So I will find out how many numbers are divisible by 19 by doing n divided by 19, right? And I see how many set bits are there in this number. So there is only one set bit. So this term will be my added to my answer, right? Maybe next time I go to some number 5 which has 1001. So this will correspond to 19. So denominator will become 19, then I skip this prime number, so 17 is skipped. I take prime number which is 13, right? So 19 into 13 will be there, and n divided by 19 into 13 I'm going to do, and since the number of terms I'm combining here are 2, so I will subtract this from my answer. And for this number you will find that all the set bits, all the 8 set bits are 1, so you will just multiply all the prime numbers. That would be a huge number, and that is the reason I'm taking denominator as long, right? So this is what we have done in this tutorial, and I hope you liked it, right? Hi everyone. So now we will discuss a concept called fast exponentiation. It's a way to compute a raised to the power n in an efficient manner. Okay. So let us say we want to compute, let's say we are given two numbers, and we want to compute a raised to the power n. Okay. So we want to define a function power of a raised to the power n. Now you know there are multiple ways to do it. One way is you um, take a loop and you multiply a n number of times. Okay, so you multiply it n number of times, and this can be easily done in order of n time. Okay, but we want to do it in a better method. So for that we will need to learn this concept of faster exponentiation. Okay, so what we can do is we can say, okay, our problem is to compute a raised to the power n. So I can break down this problem into a sub problem. Okay, so the sub problem would be uh, let's say this is equal to a into a raised to the power n by 2 and square of this term if n is odd, and this is equal to a of n by 2 square if n is even. Okay, so depending upon the value of n we can break down into a sub problem. Okay, so either we will make a call on this sub problem or we will make a call on this sub problem. Okay, so this is what a sub problem is. So clearly you can see in this you are able to reduce a problem from size n to size problem of a size n by 2, that can be reduced into a problem of size n by 4, that can be reduced into a problem of n by 8, and up to eventually we will end up at getting a problem of size 1. Okay, so basically you will be solving log of n sub problems in total. Okay, so let's see one example. Let's say you want to compute 5 raised to the power 11. Okay, so this can be written as 5 into 5 raised to the power n by 2, that's 5 and square of this term. Okay, so this can be written as 5 into 5 square and square of this term, and this can be written as 5 into 5 raised to the power 1 and square of this term. So you can see we quickly when we end up at a base case, or we can say, okay, when something raised to the power 1 is when we have the value of n as 1, we should return the number itself. Okay, so that's like a base case, or you can maybe reduce it to 0, so that you can say it is 5 into 5 raised to the power 0 and square of this particular term. So, or maybe let me give you an example of even case also. Let's say you want to compute 2 raised to the power 8. So what you can say, it is nothing but it's square of 2 raised to the power 4. It is nothing but it's a square of 2 square, and it's nothing but it's 2 raised to the power 1 and square of this term. So you can see where here we have the value of n as 8, and the number of sub problems is almost log n. So we have three sub problems. One problem computes 2 raised to the power 1, another problem computes 2 raised to the power 2, another problem computes 2 raised to the power 4, and finally we compute 2 raised to the power 8 just by squaring the previous terms. Okay, that's what we do. So we can design a recursive function that helps us to implement this. So let's say we have int a comma n, we can take input a and n, and here we can design this function. We can say, okay, if n is 0 we can return 1. So a raised to the power something is a raised to the power 0 is 1. Okay, otherwise we can check if n is odd, then we can do something, otherwise we can do for the even case. Okay, So if n is odd, so if n and 1, so I'm just checking if the last bit is 1, that means n is odd. In that case, I will compute a smaller sub problem. So let's say a small answer. Okay. So, or let's say the solution to the sub problem is nothing but it's given by calling the same function with a power of n by 2. That's that's the solution to a smaller sub problem. So if n is odd, in that case your answer is nothing but that's a multiplied with the sub problem square. So that's sub problem into sub problem. Okay. Otherwise, if n is even, then you can say okay, you have to return sub problem into sub problem. That's it. And this is the fast power function. So the complexity of this function will be order of log of n, and it is better than doing the order n loop. Okay, so here we are saying okay, a raised to the power n is nothing but a into a raised to the power n by 2 and square of this term when n is odd. That's what we have written, and it is simply a raised to the power n by 2 square of this term if n is even. That's what we have done. Okay, so now let's test our code. Okay, so let's build our code and let's try to run it. So let's say we give 5 and 3 as input, so we get 5 raised to the power 3, that's 125. Let's say 2 raised to the power 10, that's 1024. So it means this is working perfectly fine. Okay, so that's all for this video, and see you guys in the next. Hi everyone, in this section we are going to start solving problems involving linear recurrences. Okay, so what is a linear recurrence? Let me give you a very simple example of a linear recurrence. For example, this Fibonacci series is a linear recurrence. Okay, and the question will be of something of this form: given a linear recurrence, you need to find nth term of the recurrence. Okay, so these type of problems are quite common, and you may have different type of linear recurrences. For example, this is a linear recurrence, even this is a linear recurrence. Okay, so what actually is a linear recurrence? So in linear recurrence is a function, okay, is a function in which each term of the sequence is a linear combination of previous terms. Okay, it's a linear combination of previous terms. So that means you can define each term in as a function of previous terms. Okay, so that function must be a linear function, that cannot be a quadratic function. Okay, for example, if I say f of I equals to f of I minus 1 multiplied by f of I minus 2. Okay, so here you are defining each term in terms of previous terms, but this is not a linear recurrence. Okay, but this is a linear recurrence because you are adding these terms. Okay, so this is actually a quadratic term. Okay, you are multiplying two terms. Okay, so this is not a linear recurrence and this is a linear recurrence. Okay, so this is a function in which each term is defined, each term of the sequence is a linear combination of previous terms, and you might be asked to compute what is the next term. Okay, for example, if you take example of Fibonacci, then there are multiple ways to compute the nth term. So the very basic way is you can use a recursion that needs exponential time complexity, or you can do it using two or three variables, that's kind of a dp, and if you use dp, that's order of n time. Okay, but we will learn about a technique in this section that is especially used to solve linear recurrences, that's called as matrix exponentiation. Okay, and this matrix exponentiation will help you to solve this Fibonacci sequence in k cube log n time, and for the case of Fibonacci the value of k is actually 2, so you can say it's 8 log n or it's order of log n. Okay, so let's discuss this technique and what are the steps involved to solve this kind of a sequence, or these kinds of problems. Okay, so let's discuss the first step. So in the first step you have to find out the value of k. Okay, so the value of k, basically what is k? So k is the number of terms on which f of I depends. For example, if I give you this term, this sequence, so f of I depends upon the previous two terms. So for the case of Fibonacci, the k is 2. Suppose I add another term, f of I minus 4. What will happen in this case? So in this case, f of I depends upon f of I minus 1, f of I minus 2, f of I minus 3, and f of I minus 4. Okay, so f of I minus 3 is not explicitly written here, but you can say it is 0 times f of I minus 3. Okay, so the current term is also depending upon the fourth last term. So value of k in this case will be 4. It will not be 3. So k will not be 3. K will be actually 4. So this is how you find out the value of k. Okay, once you know the value of k, the next step is you need to find out the first k terms of the sequence. Okay, so the next step is find out the first k terms of the sequence. Find out first k terms of the sequence. Okay, for Fibonacci we know the first two terms of the sequence is 0 and 1, and let's call this as f1 vector. Okay, so let's call this as f1, the first k terms of the sequence, and that must be given in the problem. Okay, because if you want to compute nth term of the sequence, you must know the first k terms of the sequence. Okay, the step 3 is you need to find out a transformation matrix. Okay, so you have to find out a matrix T that is of the size k cross k, and it's called as transformation matrix. Okay, so let me tell you uh, why this is called as transformation matrix. Okay, transformation matrix. So basically it will be a 2 cross 2 matrix such that when it is multiplied by f of I. Okay, so f of I denotes uh, the ith Fibonacci number and the next number, let's say. Okay, so for example, f of 1 denotes the first Fibonacci number and the next number, let's say this is f of 1. So when you multiply transformation matrix with f of I, you should actually get f of I plus 1. That means the I plus 1th Fibonacci number and the next number. For example, I will explain you. Okay, so let me draw the transformation matrix for Fibonacci, and I will explain you what it is. Okay, and how does it generate the next term. So this matrix is 0 1 1 1. So we will understand how this matrix is calculated later on, but let's see. This is the transformation matrix for Fibonacci, and here I have something called, let's say, f of I minus 2, and here I have f of I minus 1. Okay, so I put the smaller term on the top and this term on the bottom. Okay, so let's say f of I depends upon these two terms, let's say I minus 2 and I minus 1, and what I will get. So if I multiply these two matrices, so if I say 0 into f of I minus 2 plus 1 into f of I minus 1, we will get f of I minus 1 on the top, and if we do something like this, so this will be nothing but f of I minus 2 plus f of I minus 1, that is f of I. Okay, so this is what you get. So you can see if you have terms like these, f of I minus 2, f of I minus 1, and then you get term f of I. Okay, so if you multiply these two terms with the transformation matrix, then you get these terms. Okay, then if you multiply these two terms with the transformation matrix, you will actually get f of I plus 1 also. You can verify it yourself, that if you put if you do something like this, 0 1 1 1 multiplied with f of I plus I minus 1, and if you put f of I here, then what you will get? You will get f of I on the top, so f of I will come here, and basically you are discarding the previous term. Okay, so in this case, the previous term is f of I minus 1, and you're adding up the last two terms to generate the next term. So if you add f of I minus 1 with f of I, what you will get? You will get f of I plus 1. Okay, so what happens is, in order, the general formula is something like this. If you want to compute the nth Fibonacci, let's say f of n, so that can be written as t times f of n minus 1. Okay, and how do you compute f of n minus 1? That can be written as t times f of n minus 2. Okay, and that can be written as t into t into t times f of n minus 3. Okay, and it can be written as t raised to the power n minus 1 into f of 1. Okay, so this is the whole idea. Okay, so you can see f of n can be computed as t raised to the power n minus 1 into f of 1. So here what you are doing, so you have a k cross k matrix. Okay, and you're computing the nth power of that particular matrix. You have some numbers here. Okay, and that power can be calculated using fast exponentiation. And if you do fast exponentiation, you know it is going to take log n steps, and at every step what you need to do, you are saying, okay, I have a matrix M, I want to compute the nth power. So I break it into a sub problem where I compute m raised to the power n by 2, and I multiply it with the same matrix with the same result, that is m raised to the power n by 2. Okay, to get m raised to the power n. So you can see during this step you are also multiplying two matrices of the form k into k into k. Okay, so when you multiply two matrices, you also perform matrix multiplication in k cube time. So the overall complexity of this method is going to be order of k cube log n. Okay, so if this is not clear, let me explain you with the help of one more example, that is the Fibonacci example here. So let us see how we can build up f of n step by step. Okay, so let's see, transformation matrix is given as 0 1 1 1, and let us first have the first two terms of the Fibonacci. So we have 0 1 here. So if you see what you will get here, you will get 0 into 0 plus 1 into 1, that is 1 here, and you will get 1 into 0 plus 1 into 1. Okay, that is also 1. So Fibonacci sequence is like this. Okay, now if you multiply this result with the transformation matrix again, okay, so that's 0 1 1 1, and if you multiply this result 1 1, what you will get? You will get 0 into 1 plus 1 into 1, that is 1. So basically this term is removed and this term moves to the top. Okay, and 1 into 1 plus 1 into 1, you get 2. Okay, so if you multiply the next output with the transformation matrix again, that's 0 1 1 1. So what do you do? 0 into 1 plus 1 into 2. So you basically remove this 1 and you move this 2 up and you generate a new term here. So that's 1 into 1 plus 1 into 2, that's 3. Okay, so you can see we first had 0 1, from there we generated 1 1, and from where we generated 1 2, from there we generated 2 3, and if you keep on doing this, you will see you are able to generate Fibonacci terms in this f1 vector. Okay, so the way we are not going to do it in a linear fashion because it's going to take so much time, we can actually use the exponentiation property of the matrix. Okay, so we have 3 here and we have 5 here. Now you can see we are able to generate 3 and 5. Okay, so instead of doing it like this manner, that we generate the next term, we multiply it with t, then we generate the next term, multiply it with t, we can directly say that f of n can be written as t raised to the power n minus 1 into f of 1. Okay, so we can compute this power in order of k cube log n time, and we can multiply it with f1. Okay, so this is a general idea of matrix exponentiation. Okay, so this is the whole idea, and we can use it to do exponentiation on different type of sequences as well. Hi everyone. So now we will discuss how do you actually find the transformation matrix. Okay. So let me start with the recurrence. Let's say f of I equals to f of I minus 1, and let's say this is 1 into f of I minus 1 plus 2 into f of I minus 2 plus let's say 0 times f of I minus 3 plus let's say 4 times f of I minus 4. Let's say this is a recurrence, so let's say this is a example recurrence. So you can see it is of the form, a general form is of the form c1 into f ci into f of uh, let's say cj into f of I minus j. Okay, and we have a summation where j goes from 1 to k. So this is a general form of the recurrence. So cj denotes the coefficient. Okay, so we have, this is the general form of the recurrence. Now let's see, we want to build a transformation matrix for this type of example. So firstly we need to find out f1 vector, or let's say just the fi vector. So fi vector will have all these terms, okay, without their coefficients. So we will have f of I minus 4. So the smallest term will be on the top, f of I minus 3, f of I minus 2, and f of I minus 1. Okay, and what you need to do is, when you multiply this with the transformation matrix, okay, so it will be a 4 cross 4 matrix now, because the value of k here is 4. What you should get is, you should get a new vector in which you have the next 4 terms of the sequence. Okay, so you have the next 4 terms will include these 3 terms and f of I. So ideally what you should get is, you should get a f of I minus 3 here, f of I minus 2 here, and f of I minus 1 here, and finally you should get f of I here. Okay, so now given this and this, we can actually see how we can build this matrix. Okay, so what you need to do, so basically when you multiply this row with this particular column, what happens? So all the terms should vanish except for this term, so we can just put it as 0 1 0 0. Okay, so that's how you will get f of I minus 3. Okay, so when you multiply this row with this column, what you should get? You should get f of I minus 2. That means the coefficient of f of I minus 2 should be 1, rest all terms should be 0. So this is what it is. And similarly this term should be 0 0 0 1. Okay, so when you multiply this row with this column, you will get f of I minus 1 here. Let us discuss about the last column, what it should be. So in the last column, what it should be of the form. So here you want to build f of I. So what is f of I? F of I is nothing but 1 times f of I minus 1. That means the coefficient of this term should be 1, plus it is 2 times f of I minus 2. That means the coefficient for this term should be 2. So it is 2, then it should be 0, then it should be 4. So if you carefully see, if you now multiply this row with this column vector, what you get? You get 4 times f of I minus 4 plus 0 times f of I minus 3 plus 2 times f of I minus 2 plus 1 times f of I minus 1. That is nothing but it is equal to f of I. So this is how you can actually build a transformation matrix logically. So this is the logical explanation for the thing. Okay, but if you want to find out a generalized trend, okay, if you see the general trend, if you are given a recurrence like this, okay, if you're given a recurrence like this where you have uh, c1 followed by f of I minus 1, so it's of the form c1 into f of I minus 1 plus c2 into f of I minus 2 plus up to ck into f of I minus k. Okay, so if you want to write the transformation matrix for this form, so the generalized matrix will look something like this. So it is of the form k comma k. So the first, okay, so the first column here, it will be zeros except last row. Okay, and what you will do, you will try to build a identity matrix. At this point you have 1 1 1 followed by 0 0 0 0 and 0 0 0. Okay, So something like this. Okay, we have four, 1 2 3 4. Okay, so this is not there. So you can see this is actually an identity matrix if you leave the first column, or you can say this is an identity matrix in which you have prefixed a column of zeros. Okay, that basically shifts all the matrix of the all the elements of the identity matrix one step towards right. And if you talk about the last row, so the last row will contain nothing but the coefficients of these terms, but in the reverse order. So you will have C1 here, you will have C2 here, and you will have ck here. Okay, that will make sure that you multiply terms in the correct order. Okay, so this is how a generalized matrix will look like. So you have uh, coefficients in the reverse order in the last row, and you have a identity matrix on the top and prefixed with a column of zeros. That's how it is written. Okay, so now if we try to write a matrix for this, we know it will be a 4 cross 4 matrix. Okay, so we will first reserve the last row for the coefficients, that's 1 2 0 and 4. So we put these coefficients in the reverse order and we put zeros here, and rest all positions we can fill with the identity matrix. Okay, so now you can see this is the exact same matrix that we have derived logically here. Okay, so this is how you can directly generate transformation matrix. Okay, so one variation that may arise is you may have a constant term here, let's say plus d. Okay, d is a constant. Then what you can do, let's see. Okay, so in that case it will be of this form. Okay, let's try to build it again. So let's say we have f of I minus 4, we have f of I minus 3, we have f of I minus 2, we have f of I minus 1, and we have a d here. Okay, and what we need to build is we need to build f of I minus 3, f of I minus 2, f of I minus 1, f of I, and a d here. Okay, so this is what you need to build. So clearly if we see what will be the size of identity matrix transformation matrix, now it will be 5 cross 5. Okay, so what will be the coefficients of the first row? So we just need this term, so it will be 0 1 followed by 3 zeros. For the second row it will be 0 0 1 0 0. For the third row it will be 0 0 0 1 0. For the fourth row, now you if you want to see what is f of I, so f of I is made by combining these terms. So here we must also specify the coefficient for d. Okay, so we will have all the coefficients in the reverse order, that is 1 2 0 and 4. We should also put a coefficient 1 for d. Okay, so this 1 is for d. Now if you multiply this row with this column, so what do you get? You basically get this recurrence and that generates f of I. Okay, and what will be the final output? So you need to multiply something with this vector so that you get a d. So that will be nothing but 0 0 0 0 1. Okay, so what change we made? We added a column here, the last two elements of the column are 1, and we added a row here. Okay, so this is what we have done to accommodate this change of d. You can see, you can verify this is the correct transformation matrix when you also have a constant d here. Okay, so d is a constant. So this is how you can make modifications in the transformation matrix if the general formula does not fit. So we will see one example in the next video where we will implement matrix exponentiation algorithm on a problem. Hi everyone. So in this video, we are going to solve a problem SCQ from Spoj. It's a problem based upon matrix exponentiation and just implementation of matrix exponentiation. Okay. So it says you're given a sequence in which the ith term of the sequence depends upon the previous k terms. So you're given the values of these coefficients from C1 to Ck. And also you're given ai equals to bi for I less than equal to k. Okay. So if you want to compute the ith term, and for all values of I that is less than equal to k, you are given those values in the form of bi. So you are basically given two arrays, array b that contains the first k terms of the sequence, and another array that is C that contains the coefficients of the terms in the recurrence. Okay, so we have to find out the nth term of the sequence. Okay, and that n can be of this order 10 raised to the power 9. That means an order n solution will not work, so we have to do it in order of k cube log n time, and that can be done using matrix exponentiation. Okay, so let's see how we can solve this problem. So I will start by taking input the data that is given in the problem. Okay, so firstly I will write the main, and in main I will accept the number of test cases. So for each test case I need to take input the value of k, how many terms I have, followed by we have to take input the value of b, that is an array that contains uh, the f1 vector. Okay, so the first k values for int I equals to 0, I less than k, I plus plus, I can say okay, seen whatever is the number that is given, and I can say b dot push back that particular number. Okay, so I'm storing that b as a vector. Okay, and after that we have to accept coefficients. So let's accept coefficients for int I equals to 0, I less than k, I plus plus. I can accept the ith coefficient, so I can push that coefficient in a vector called c that I have already created. Okay, so after that we need to compute the nth term of the sequence. So we need to input the value of n, and we can say seen n, followed by we can just make a function that's compute, that is going to compute the value of n, and we are done. Okay, and for each test case we need to clear the vector by writing b dot clear and c dot clear. Okay, so that's basically the input part, and we have a return 0 here. So that almost finishes the main part. Now let's write all the functions that are actually needed for matrix exponentiation one by one. Okay, so the first function that we will need is this compute function. Okay, so that will actually do matrix exponentiation. Okay, so here what we can say is we can have a base case. If the user is asking for a term n that is equal to 0, so the zeroth term is 0 in this case. Okay, and if n is less than equal to k, that means it is asking for a kth term. Okay, so we can just say okay, that term is already there and it is in the vector b of n minus 1. Okay, for example, if someone queries for the first term of the Fibonacci, that's already computed. Okay, because you know the first two terms, so that's you directly return the term from the bth array because that contains the first k terms of the sequence. Otherwise we actually have to compute the nth term using matrix exponentiation. Okay, otherwise use matrix exponentiation. So what I will do, I will create a vector that I will call as f1 vector, and it is of the size k plus 1. So basically I am doing indexing from 1. You can also do indexing from 0. So it's a vector that stores the first element at index 1. So what I can do is for int I equal to 1, I less than equal to k, I plus plus, I can just initialize this vector by saying f1 of I equals to b of I minus 1. So basically user has given me, question gives me input, let's say the first values are 1 2 3. So I make a f1 vector that's like a vector, and I store in the first index 1, in the next index 2, and in the third index 3. So it's like 1 2 1 3. Okay, so these are the indices and these are the values that are mapped. And the b array, the b vector is indexed from 0, so that's why I have done f of I equals to b of I minus 1. So this is my f1 vector, that's my step 1. Okay, and next step is you need to build the transformation matrix. So let's build the transformation matrix. So that matrix can be represented as a vector of vector. So that's a 2D vector now. And let's say we have a matrix uh, whose size is k plus 1, and every element of that matrix is basically a matrix is a vector of size k plus 1. Okay, so what I am doing is, so this basically creates k plus 1 vectors, and they are initialized with every element of that matrix is a vector in itself. Okay, so this is how I can create a 2D vector. Okay, that's like a vector of vector. So reason why I'm taking it as of the size k plus 1, because the first index that I'm going to say is, it will be 1 comma 1. Okay, so I'm making it from 1 comma 1 to k comma k, and I'm just ignoring the 0th row and the 0th column. If needed, you can also make it of the form k comma k, that's also fine. Okay, so now let us try to put elements inside this uh, transformation matrix. So as I discussed, we will use the generalized formula to put the elements. So we will have a identity matrix in all the rows, a shifted identity matrix except for the last row. Okay, so I can say if j is less than equal to k, j plus plus. So I will have two cases. If the row number is less than k, then I will do something. Okay, but if the row number is equal to k, then I will do something else. So I can just put an else block here. Okay, that will be the case when I will be equal to k. So if I is less than if I is less than k, then we have to fill zeros and ones. Okay, and also we need to fill one at a particular position. So that position will be if j equals to I plus 1. In that case, t of ij will be equal to 1, otherwise it will be 0. So I can say t of ij will be equal to 0. So that's it. And finally, for the last row, that in that row I will put the coefficients in the reverse order, that will be equal to c of k minus j. So this is how I put the coefficients in the reverse order. Okay, so if you have any doubts here till now, before we move on to the third step, let me just make it clear. So what I've done is, let's say it's a 4 cross 4 matrix. So I have put 0 1 0 0 0 0 1 0 0 0 0 1, and I have put c1 c2 c3 c4. Okay, at this row I equals to k, and also for this part I'm checking if j equals to I plus 1. So this index is 1 comma 1, this index is 1 comma 2, this index is 2 comma 3, this index is 3 comma 4. So at all such indices you can see the value of j, this is j, this is equal to value of I plus 1. So if this is the case, I put that element as 1, otherwise I put all elements as 0. So this is how I build a shifted version of identity matrix. So now we have to go to the third step. In the third step, we need to compute the power of the transformation matrix. So we need to create a power function that will do the exponentiation for us. Okay, so for example, if you need to compute Fibonacci, then you need to compute the n minus 1th power of this particular matrix 0 1 1 1. Okay, so we will write a function that will actually uh, compute this. Once we get the output matrix, that will be again of this form a b c d, we can multiply it with f1 vector to get the final result. Okay, so that we can actually do. So now let us write the power function, and fourth step we can write later. Okay, so let's write a power function now. Okay, so power function will also accept a vector and it will return a vector. Okay, so vector will be a vector of vector, and let's call it as power, and it's vector of vector, and let's call this matrix as A, and let's call that power as P. Okay, and here in the base case we can see if P is 1, if the power is 1, we can just return that matrix. Okay, otherwise we can check if the power is odd, if the power is odd. So what we can do is, if you want to do a raised to the power, let's say p, you can say if p is odd, okay, you can say this can be written as a into a raised to the power p minus 1, and in this case p will be even, then I can say a raised to the power p can be written as a raised to the power p by 2 and square of this term if p is even. So you can see we are actually using a divide and conquer algorithm to reduce our problem into sub problems, and those sub problems can be solved in less time. Okay, so if you want to compute a raised to the power 8, then it can be broken into a raised to the power 4, it can be broken down into a square, and it can be broken down into a raised to the power 1, and we have a base case if the power is 1 we just return a. Okay, so this is how it will actually take log of n steps to compute the power of the matrix. So we can say if power is odd, so we check the last bit of p, I can say return. What do you return? You multiply a into a raised to the power p minus 1, so that power will be computed by the recursive function. So this, but you cannot do direct multiplication because it's not a number, it's a matrix, so we need to write a matrix multiply function that we need to call at this particular point. Otherwise we just know that p is even, so we can just say okay, let's create a matrix x that will store the answer of a raised to the power p by 2. Okay, so let's call this matrix x as power of a raised to the power p by 2 since p is even, and our final answer will be nothing but if you multiply this matrix with itself, that will give you a raised to the power p. Okay, so this completes our power function, and now we have to write one more function, that is the multiply function. Okay, so that function will again accept two matrices and it will return their product. So we are assuming that those two matrices are k comma k matrices. Okay, because we are multiplying the same matrix with itself, and the dimensionality of those two matrices will be same, because if you multiply a with some power of a, so both of them are square matrices, so every time the dimensionality will be k comma k and the time taken will be k cube. So we get a matrix called a, and we also get a matrix called b. Okay, now let's write the logic to multiply matrices. Okay, so let me give you quick recap of matrix multiplication. Okay, so what you do, you iterate over this row, you iterate over this column, you do element wise multiplication of these elements with these elements, and you finally sum it up and you get an element for this particular position. Similarly, you multiply this row with the next column and you get this particular element, and so on. Okay, so this is how you do matrix multiplication. Okay, so let's first write the logic for int I equals to 1, I less than equals to k, I plus plus, so on. Okay, for int j equals to 1, so iterate over all the rows, for every row you iterate over all the columns and all the columns of the second matrix. Okay, so what I need to do is I need to form a sum. Okay, so we have uh, to create a matrix to store the result. Okay, so let's store the result in some matrix C. So clearly you have A, we have B, so I'm going to create a local variable here that is different from this. Okay, so this global variable is a 1D vector, but here I'm going to create a matrix called C that is of the shape k plus 1, and every element is a vector of the shape k plus 1. Okay, so it's like a 2D vector, and now you can see C of ij, that is the element in the ith row and the jth column of this C matrix will be sum of my previous sum whatever I have plus the output of my current multiplication. Okay, so in the current multiplication what you do, you pick the uh, okay, so we actually have to put one more loop. Okay, so not here, we cannot do it like this, so let's put a loop to iterate over all the elements of that particular row and column. Okay, so there is a variable x that goes from 1 to k, and I do x plus plus here. So I say c of ij equals to c of ij plus, you pick the element from the ith row, xth position, multiply with the element from xth column, uh, xth row, and the jth column from the b array, and you also do a mod at every step in order to avoid overflow, because this is given in the question, and modulus has this property. Okay, so we are using the modulo property here as well, that a mod b is same as doing a plus b mod b is same as doing a mod m plus b mod m and whole mod m. Okay, so this property we are using here in order to avoid overflow. And let me just give you what we are doing. So we are on this row, and let's say this column, so we take a variable x that iterates over all the elements of this row, and what I do is I compute c of ij. So this is c of ij, so I multiply a of ix. So I is 1 here, let's say j is 1 here, and x is going over all the elements here, and x is also going over all the elements here. So I'm multiplying them, taking mod, adding to my sum, and finally my total sum will be this multiplied by this, and in the second array. Okay, and this will be stored in the third array, that is c of ij. Okay, okay, so this is a, this is b, and this is c. Okay, so I just remove it here. So this is nothing but simple matrix multiplication. I hope you already know that. So finally, from this point I can return the matrix C. So this is the function that multiplies two matrices. Okay, and now we are left with the fourth step, where we have to do a matrix, and we have to multiply matrix with a vector. Okay, so we have to multiply matrix with a vector. So now let us do that multiplication in order to get our final result. So let's say now you have done t raised to the power n minus 1. So suppose now you get this particular matrix a b c d, and you have f0 vector at this particular point, or f1 vector at this particular point. So you will get f of n. Okay, so let's say this term is f of n, this term is f of n plus 1, and so on. So what you need to do, you need to do this multiplication. You multiply this row with this particular column to get this particular value. Okay, so instead of writing the entire matrix into vector product, I can just do multiply the first row with the first column, or the only column of f1 vector, to get the fn value. Okay, so that's how I'm going to do it, and we will have up to f of n plus k values, something of this form. Okay, so let's just multiply the first row with the first column. So let's say I have a result that is equal to 0, and for int I equals to 1, I less than equal to k, I plus plus, and I can say result equal to result plus t of 1 of I multiplied by f of f1 of I, and I take a mod here, and I take a whole mod here. Okay, so here I should have a bracket and a whole mod here. Right, this should be like this. Okay, and I can say return result. So if you carefully see, what I have done here is I've taken the first row of the transformation matrix, I iterates over the columns, multiplies with the ith element in the f1 vector, and takes the mod at every step to calculate the result. That is just the f of nth term. So I'm not computing the entire vector, I'm just computing the nth term by multiplying this row with this column from the transformation matrix. Okay, because this is what it is needed. And finally we return the result, that is now the nth term of the sequence. So these are all the steps, and now we will try to run the code. So now I will test my code on the sample input. Okay, so I copied my input, and let's try to run the code, and I give the sample input, and here I get the sample output. Okay, so the last three lines here, so it is 8714 and 21 this, so it's 8714 and 514. So that means our code is correct, and this is how we can actually do matrix exponentiation. Okay, so it's totally fine. Okay, so that's all, and I hope you got an idea how you can implement matrix exponentiation. Hi everyone, so now we will discuss another problem, that is SPP recursive sequence 2 from Spoj. Very interesting problem. So the first part of the problem is same as SEQ. It says there is a sequence in which the ith term of the sequence is a linear recurrence in terms of previous k terms, and this is the same sequence that we have discussed in SEQ. But in this problem you have to compute sum of terms am to an. That means here each term is also sum of past previous terms. Okay, so you need to compute the sum of terms from am to an. Okay, so earlier you just needed to compute the a of n. Now you have to compute sum of terms. Okay, where m and n lie in a very large range. Okay, so if m is 1, n is 10 power 18, that means you cannot iterate over all the terms. And if you also compute all the terms, let's say in k cube log n time, then if you just find the sum, that is going to take 10 raised to the power 18 into this much time. So this is practically not feasible to compute this particular sum. So you have to think how you can approach this kind of a problem now. Okay, so if you try to analyze this, so clearly if you have seen something like a cumulative sum. Okay, so if you somehow maintain a sum s of n that denotes the sum of all the terms from, let's say, a1 to an. Okay, and we can say, okay, s of n can be written as s of n minus 1 plus a of n. Okay, that's how you can define s of n. And if you want to compute this sum from am to an, you can say, okay, I can just find out the sum till n terms, that is s of n, and I can just subtract the sum till s of till m minus 1 terms, that is s of m minus 1. So you actually need to find out this. So if you know these values, you can do the subtraction, and s of n is nothing but sum of terms from a1 to an, and s of m minus 1 is nothing but sum of terms from a1 to a of m minus 1. And if you just do the subtraction, you will end up getting sum of these particular terms, that is sum of am to a of n. Okay, now this is the modified problem statement. Okay, so if you need to compute uh, this sum, you actually you should compute sum of sum till n terms. Okay, so this is now the modified problem statement. So let me give you a hint how you can approach this problem is. Okay, so let's discuss a hint to solve this problem. So I need to say that s of n is something that I need to compute, and s of n is also a linear recurrence. How it is a linear recurrence? Because it can be written as sum of or let's say s of n plus 1. Okay, so s of n plus 1 can be written as sum till n terms plus a of n plus 1. This is what you can say. And also it is given that a of n plus 1 is a linear recurrence. Okay, so a of n plus 1 is nothing but it's c1 times a of n plus c2 times uh, a of n minus 1 plus c3 times a of n minus 3. Okay, a of n minus 2, sorry, and so on. Okay, so this is how this is being defined. So, and up to ck times a of n minus k minus 1. Okay, or n minus k plus 1. So something of this form. This is already given to you. Now you have to think how you can build a transformation matrix and how you can build a f1 vector for this. Okay, so a hint to solve this problem is you can say, okay, if you talk about the fn vector, that can be written as something of this form. Okay, so that contains a term sn, that also contains a term that is this thing a of n. Okay, so the smallest term is a of n minus k plus 1, so it is a of n minus k plus 1, a of n minus k uh, plus 2, up to a of n. Okay, so these are the terms that will go here, and now you figure out what is the transformation matrix. And also what you should get here is, you should get is s of n plus 1. Okay, and here you should get a of n minus k plus 2, a of n minus k plus 3, and finally you should get a of uh, n, and you should get a of n plus 1, something of this form you should get. Okay, so now let's see how you can generate this particular term. So we need to figure out what should be the coefficients in the first row. So in the first row, uh, to make s of n plus 1, you need s of n, and also you need all these terms. Okay, so clearly this coefficient should be 1. Okay, and followed by, you should have a coefficient for this particular term. Okay, so for this particular term, you know the coefficient should be equal to c of k. Then for this particular term, the coefficient should be equal to c of k minus 1 up to c1. So in the first row, if you put these terms, you will be able to generate s of n plus 1, because you are adding s of n and you are also adding these terms multiplied with their coefficients. Okay, and for the next row, you can just do this thing, you can do a shifting. So you can say 0 1 0, sorry, it should be 0 coefficient for this, 0 coefficient for this, 1 for this, so it should be 0 0 1 0 0 0. Okay, so it's also a shifted version of uh, this matrix. Okay, and it goes on except for the last row. Okay, so in the last row, you have to make from a n, you want to make a of n plus 1. So again, what you will do, you will put a coefficient of s of n as 0, followed by coefficient of this term. So this term has a coefficient of ck, so it will be again ck minus 1 till c of 1. So if you multiply these coefficients with these terms, you will end up getting a of n plus 1. Okay, so this is how a of n plus 1 is defined. So I hope you will be able to build a transformation matrix now, and you will be able to build the code for it as well. Okay, so that's all for this video, and thanks a lot. Hi everyone. So now we will discuss a problem called as ladder's problem. So in this problem, you are standing at this particular end, that's the ground location, and you want to reach on the top of ladder that has n number of steps, and it's also given at every step you can take a jump of 1 2 or 3. Okay, that's given. So that means you can jump one step, you can jump two steps, and you can jump three steps, and that you can do at every step. So we want to find out the number of ways to reach n. Okay, so we want to find out the number of ways in which we can reach n. For example, if let's say n is 4 and the maximum jump size is actually given as k, and let's assume the k is 3. Okay, so what we can say is, in order to reach 4 steps, one way would be we can take one step each time, or we can take 1 to 1 steps, or we can take 2 1 1 steps, or we can take 1 1 2 steps, or we can take 2 2 steps, or we can take 3 1 steps, and we can take 1 3 steps. We cannot take a jump of 4 because the value of k, that is the maximum jump, that is 3. So we have 1 2 3 4 5 6 and 7 ways. So this is my output in this case. Now you might think, how do we compute such an answer? So let us assume that in order to reach the final step, let's say the number of ways is f of n. Okay, and we need to compute what is f of n? We need to define a recursive relation. Okay, now suppose you are standing at this particular point, so from what all steps you can reach this particular point. Okay, so one way is you are standing at this point and you take a jump of 1 and you reach this particular point. Okay, so that means all the ways to reach this point will also be the ways to reach this particular point. So that means f of n should be at least equal to f of n minus 1. That's the one observation. Okay, also you can also take a jump of 2 from this particular point and you can reach this particular point. That means you can also you can also take a jump of 2 from this point and you can reach all the nth step directly by taking a jump of 2, and from here by taking a jump of 1. So that means all the ways in which you can reach this location, so these ways will be added to this answer. Okay, so this will be f of n minus 2. Okay, now some of you might think, okay, what about these ways in which we are going to this location and then going forward? So all those ways are already counted when we computed f of n minus 1. Okay, and also we can take a jump of 3 from this location and we can reach to the top of the ladder directly without stopping at any of these steps. So that will contribute, the number of ways to reach this location will be f of n minus 3. And doing this, it is possible we have to sum till f of n minus k. So this is now a linear recurrence. Okay, and this is how you can actually solve this problem. So let me just do a dry run for n equal to 4 and k equal to 3 case. So it's like a recursive relation, and now there are multiple ways to solve it. If you do it using recursion, it will end up getting a exponential complexity. If you use dp, you can do it in, I think, linear or an order of n into k time, and we can see we can actually solve it using matrix exponentiation, and that can be done in order of k cube log n time. So let me just give you an example where we can dry run this recurrence. Okay, so let's say n is 4 and let's say k is 3. So 4 means you will make 3 calls, 1 on 3, 1 on 2 and 1 on 1. From 3 you will make 2 calls, 1 on 2, 1 on 1, 1 on 0. From here you will make 2 calls and we make a call here. Okay, so we are not going beyond 0. Okay, we are not going beyond 0. So at this is a base case. Now at 0 we stop. So 0 will return one way and 1 will return one way, because there is one way to stand on the ground. So n equal to 0 means you are on the ground and there is one way to stand on the ground. So 0 returns a 1 here and 1 also returns a 1 here, and 0 will return 1 here, and 2 will return the number of ways to reach 2 from 1 and from 0. So and you will do sum of these two, so that is 2 ways. Okay, so similarly you will return 1 here, you return 1 here. So 3 will return the number of ways to reach 3 from 2, which are 2 plus 1 plus 1. So it is 4 ways. Similarly from 2 you will return a 2, and similarly from 1 you return a 1. Okay, so the number of ways to reach 4 via 3. So if you stop at 3, there are 4 ways. For example, this is one way, 2 1 is one way, 1 2 is one way, and 3 is another way. So if you stop at 3, so these are the ways in which you first stop at 3 and then you go to 4. So there are 4 ways. Okay, if you stop at 2 and then you go to 4 by taking a direct jump, there are 2 such ways. So number of ways to reach 4 will be 4 plus 2 plus 1, that is 7. Okay, so I've given you a hint how you can solve this problem. So the whole idea was here was, it is possible that you might not be given the recurrence in the problem, but you have to come up with a recurrence on your own and then solve it. Okay, so this question is now an homework for you. You can apply your matrix exponentiation, you can build the transformation matrix T and solve this problem using matrix exponentiation. So thanks a lot, see you guys in the next video. Hi everyone. So we will discuss about one principle now that is called as pigeonhole principle, okay? And I will show you in some examples in coming videos how this principle can be used to solve some of the problems, okay? So very simple principle and it's a very logical principle you can say, okay? So it's very easy also, but it might be little tricky to think how this principle is being applied to solve some of the problems that we will discuss in the coming videos, okay? So this principle says, suppose if you have p pigeons, okay, or let's say you have p plus 1 pigeons and you have p number of holes, then if you want to put these pigeons into these holes, let's say you have 4 holes and let's say you have 5 number of pigeons, okay? So if you want to put these pigeons in these holes, then there will be at least one hole which contains at least 2 pigeons. That's what it says. So clearly you can say if you club these pigeons into 4 holes, then at least one hole will have 2 pigeons. Now you may say, okay, this is the most obvious thing that we can have. Okay, so how this can be used in solving some of the problems? Okay, so let me give you some numbers. One very simple example you can say. Let's say in Delhi you have lot of people. You have let's say a population of let's say you have a population of 5 lakh. Okay, and let's say you want to guess and let's say on an average a human being has, let's say at most 1,50,000 hair on their head. Okay, so this is the maximum hair, let's say, that a human being can have on their head. So is it possible that two human beings in Delhi have the same number of hair on their head? Okay, so you have to guess yes or no. Okay, yes or no. So now you can think of pigeonhole principle at this point. Okay, so obviously the answer will be yes, because we have maximum of 1 lakh 50,000 here on any head, and we have a population of 5 lakh. Okay, so what do you need to do? You can say we have buckets from, let's say, numbered from 0 to 1,50,000, but we have people, or let's say we have pigeons or persons, they are numbered from p1 to p of 5 lakh. So obviously the number of people is more than the number of buckets we have. We can obviously club them into we can club two people in the same bucket. Okay, so accordingly we can say yes, it is very likely that two people can have same number of hair on their head. Okay, so this is a short introduction to pigeonhole principle, and from the next video we will discuss how this problem how this principle is used in solving some competitive programming problems. Let's see that. Hi everyone, the problem that we are going to discuss today is divisible subarrays, and it's a slightly tricky problem as compared to other problems. And let's first go through the problem statement and then we will come to the solution. So it's given you have an array that actually contains n elements. So there is an array containing n elements. We have to find the number of good subarrays. Okay, so we have to see what is the definition of good. So good subarray is a subarray that such that sum of elements of that subarray is divisible by n. So here n is the number of elements in the array. Okay, so this is what the problem is. For example, suppose you are given an array like this, and you actually want to find out how many subarrays are there such that sum of elements of that subarray is divisible by n. So n in this case is 5 because there are 5 elements in this array. So one subarray I can clearly see here, 3 plus 2, the sum is 5 and 5 is divisible by 5. Another subarray is 6 and 4. Here also the sum is divisible by 5 because sum is 10 and 10 mod 5 is 0. You also have this as a entire subarray because sum is 15 and 15 mod 5 is also 0. So you can have multiple such arrays, and we actually want to figure out how many sub arrays are there. Okay, so what you cannot do in this problem is you cannot generate all sub arrays because n is very large. So if you see, the range of n is 10 raised to the power 5, and if you generate all sub arrays, then this complexity is going to be n square, that is going to be 10 of the order 10 power 10, and this will lead to TLE. Okay, so this is why most of the students are not able to solve this problem, because they are trying the brute force approach. So we have to make use of some extra information that is available in the question, and the extra information is, you actually want only those subarrays where the sum is divisible by n, and n is the size of the array. Okay, so we will make use of this to come up with something. Okay, so slightly tricky, so we would be actually using a very simple principle called pigeonhole principle in this case. Okay, pigeonhole principle. So it's a very logical principle, and you have to see how do you use this principle. Okay, so let me show you what it is and how we can use this in solving this problem. So let's talk about pigeonhole principle first. So it says if you have n number of holes and if you have n plus 1 pigeons, okay, so you suppose there are n equals to 4 pigeons and you have 3 holes. Okay, and you actually want to allocate these pigeons into holes. So then the principle says at least one hole will have 2 pigeons, very logical thing. Okay, 2 pigeons. So this is what pigeonhole principle says. Now you might ask, how do we use pigeonhole principle here? Okay, so let us come to our array problem again. So let's say the array is 1 3 2 6 and 4, and we want to find out those subarrays where the sum is divisible by n and n is the size of the array. So how do you find out the sum? So one very basic way of finding out the sum is you iterate over that part of the array and then you add those elements to your sum. So that is inefficient. Okay, so when you have to find out sum of subarrays multiple times, one thing that you can do is you can build up an array of cumulative sum. Okay, so how do we make how do we actually make a cumulative sum array? That's pretty simple. So let's do one thing. Suppose you want to find out sum of this particular subarray. Okay, so what you will do, you will make a cumulative sum array, and that will contain the sum up to a particular index. So 0 1 2 3 4. So 0 1 2 3 4. Okay, and yeah. Okay, so what we will do, we will let's say total sum up to this point is b, and let's say total sum up to this point is a. So the sum of sub array will be b minus a, and what we actually want is b minus a mod n should be equal to 0. This also implies b mod n should be equal to a mod n. Okay, so whatever is the value of b, the same should be the value of a when you take the mod. So sum up to this point is 0, sum up to this point is 1, sum up to this point is 4, then you have 6, then you have 12, then you have 16. Now you want to find out those subarrays where this property is true. Okay, so what we will do, we will just take sum with mod n. So 0 mod n is going to be 0, 1 mod n is going to be 1, this is going to be 4, this is going to be 1, this is going to be 2, this is going to be again 1, because 16 mod 5 is going to be 1. Okay, so this is the cumulative sum array that we have generated. Now one observation that we need to make here is, since you're taking mod with n, okay, so how many values you have in this array? So you have 1 2 3 4 5 6 values. So you have 6 different values after taking mod with 5. Okay, so you have 6 different values, but we have to see how many unique values we will have. Okay, so you can have at most 5 unique values, because if you take something mod 5, okay, so there is a number x, if you take mod 5, you can get only 5 unique values. You can get 0, 1, 2, 3 and 4. So these values again we can see are from this range. So you have 6 boxes, but you have only 5 unique values. Okay, so it means at least 2 boxes will have same value. Okay, or what you can do, you can make buckets. Okay, you can make buckets. There is a bucket 0, there is a bucket or a hole 1, there is a bucket hole 2, there is a hole 3, there is hole 4 and there is hole 5. So how many values will go into 0 bucket? Only one value. How many values will go into the first bucket? Clearly you have three pigeons or 3 numbers which have the value 1. So 3 values will go in this bucket. How many in the second bucket? 1 value. How many in the third bucket? No values. How many in the fourth bucket? 1 value. And how many in fifth bucket? Sorry, this will not be there. Okay, so you only have 5 buckets. Okay, and you have 5 buckets and you have 6 values, which means at least 2 buckets will have same value. Okay, this is what I am trying to say in this case. So now the next question that you might ask is, why are we worried about the buckets which contain the same value? Because that is the key for our answer. Okay, so if you carefully see, we were actually looking for those positions where you have b mod n equal to a mod n. So in this case, you can see this is nothing but b mod n, or you can say this is nothing but a mod n. So clearly you can see these are the 3 positions where you can say if you pick any 2 positions out of here, you will get the same sum, and if you subtract 1 minus 1, you will get a sub array that actually has a sum of 0. So let us try to find out the sub array. So if you get this complete array and if you subtract this much array, so clearly this array, that is 1 3 2, and if you subtract this array, you will get one sub array that actually has a sum of 0. So b minus a mod n is getting 0 here. Similarly, you can also combine this one with this particular one, so you will get this particular sub array. So if we carefully see, this is that sub array, and this sub array has sum 15, and 15 mod 5 is also 0. And clearly you can also combine this particular one with this particular one. Okay, so out of if you have ones at m number of positions, then number of sub arrays you can pick is MC2, because you can pick any 2 positions where b mod n is equal to a mod n. So that actually leads to a 0 sub array sum. Okay, by taking mod with n. So this is another position. So if you pick this one and this one, so the elements are 6 and 4, and 10 mod 5 is also 0. So total number of sub arrays will be nothing but sum of all those positions where this sum is getting 0. So what you can do, you will just iterate over all these values, and you will add wherever you have at least 2 frequencies in that bucket. You can say your answer will be nothing but 3c2. Okay, plus 1c2 you cannot take, this is not there, this is not there, so you will skip. Suppose if you get a cumulative sum array which is like this, so you have, let's say, 3 zeros, and you have, let's say, 2 ones, and you have somewhere 4, and you have somewhere, let's say, 3. Then in such a case, it means this sub array has a 0 sum, this sub array has a 0 sum, this sub array has a 0 sum, even this sub array has a 0 sum, and this particular sub array has a 0 sum. So you have actually 1 2 3 4 5 sub arrays. So in this case, you will count there are 4 number of zeros, so we will do 4c2, plus you have 2 number of ones, you will do 2c2. So your final answer will be okay, so it will be yes, you can also have this sub array, you can also have this sub array, you have lot more options. Okay, so 4c2 is 4 into 3 by 2, that is 6 plus 1, so you will have 7 sub arrays that will actually have 0 sum. Okay, so something like this. Okay, so what you need to do in order to implement this question, you will need the values of cumulative sum mod n at every position, and you will need buckets that actually store what is the frequency of each sum. And finally, once you get the frequency of each sum, you will do FC2 and you will add this to your answer where f is greater than equal to 2. Okay, this is what you need to do in this case. So that is how you solve this problem, and now we will look at the implementation. Okay, so this problem has multiple test cases, so we will try to implement the solution now. And so I have already put a loop to handle multiple test cases. So what I'm going to do, I'm going to make a prefix sum array or a cumulative sum array. So let's just call it pre. And what we will do, we will first initialize this array with a sum of 0. Okay, so every element in the prefix sum array is going to be 0 in the beginning, and then we will start reading input. So also prefix of 0, I'm going to say it's going to be 1. Okay, one thing we can do is we can so this one thing I'm going to do is I'm not going to build this array. I'm directly going to build this, and I'm saying frequency of 0 is going to be 1 because in the beginning, if you do not consider any element, the sum of null subarray is 0. So the frequency of 0 is going to be 1. So 0 sum will come at least once because you also have a null subarray. So this is what I'm doing here. So this prefix sum is, this is not a prefix sum, this is actually the frequency array that I am having here. Okay, and then I will actually read the input. So let's iterate over all the elements. Sorry, this should be seen n. Okay, and let's try to read all the elements of the array. So I can say scene array of I, and whatever is the element I can add it to my sum. So I will create a variable called sum that is initially 0, and I can say sum plus equals to array of I, and then I can take mod with n. So sum mod equals to n, and also in some cases this can become negative. For example, if you do -5 plus 3 mod 5, this will be actually -2. So in order to make this as positive, I will add 5 to it. Okay, so I can say actually this should be like this: sum equals to sum plus n mod n. Okay, so ideally we should do this, and whatever is the sum we have made now, I can say prefix of sum plus plus. So I actually increment the frequency because I encountered one sum, and at that particular bucket I increase the count. So if you see here, so if we encounter a sum which is 1, so we increase the frequency of bucket 1 by 1. So first time you see 1, this becomes 1, next time you see 1, it becomes 2, next time you see 1, it becomes 3. So we directly build this array from our input. Okay, so let's go to the code, and after we are done with this, we actually can build our answer very easily. So we can say our answer is 0, and for int I equals to 0, I less than n, I plus plus, go to all positions and do NC2 kind of a thing. Okay, so you can say answer plus equals to pre of I into pre of I minus 1, that is NC2. Okay, or you can say int m equals to pre of I, and this is nothing but m into m minus 1, m into m minus 1 by 2. That you do, and here you do cout answer and endl. So that actually completes our code. Okay, so in the last we count over all positions and we do MC2 and we add to our answer because that is the number of sub arrays that we can make. So let us try to run this code on HackerBlocks now. Okay, so let me try to submit the code. Okay, we got one error memset. So the header file is hash include c string for memset. And let us also test our code for one test case in the terminal. Okay, so let me say dot slash divisible subarrays, and let's say I have only one test case, 6 elements, and 1 3 2 6 4. So sorry, one more element is missing, so let me do it again. One test case, 5 elements, 1 3 2 6 and 4. So yes, we are getting 3 subarrays. So one is this array 3 2, another is 6 comma 4, and another is this particular array. So we have 3 subarrays actually. And okay, so we got wrong answer in one of the test case, so probably it could be a long int problem. Okay, let me just say this is ll, and that should solve the issue, because the constraints are large and also AI can be negative. Okay. So that's why we are doing two things. We are taking everything in long, and we are trying to solve this. Okay, so we have solved the problem, and you have to be very careful, because when you multiply two numbers and they're of the range 10 per 9, that will actually lead to overflow in the end. Okay, so you should be very careful with the data types as well. So I hope you understood the logic of this problem, and you will be now able to solve it. So thanks a lot, guys. I will see you guys in the next video now. Okay, bye bye and keep coding. Hi everyone. So in this example, we will discuss a problem from CodeChef, that is divisible subset. So let's go through the problem statement. It says you are given a multiset of n integers. Okay, so multiset means the numbers in the set can repeat. We have to find a non-empty subset of it. That means it should contain at least one element such that sum of subset elements is divisible by n. So we have to find out a subset out of it such that sum of elements of that subset is divisible by n, where n is the size of the set. And otherwise we have to state that this kind of a subset does not exist, and in the output I will print -1 if the subset does not exist. If the subset exists, we will output two lines. One is the size of the subset, okay, and the second line denotes the indices of the multiset from where the subset starts. Okay, so okay, list of indices of the multiset that form the subset. Okay, that what we have to print. So also, if there are several subsets, you can output any. Now this problem is about checking if there is a subset or not that has sum of elements divisible by the size of the subset. Now you can see there are three different types of constraints. Okay, so and there are different points associated with each of the constraints. Okay, so for example, if you have a smaller constraint, for example n equals to 15, you can actually find out all the subsets in exponential time, and then do a linear pass through them in order and time to check how many subsets are there or what subsets follow this property. So you will get 37 points using a brute force search. Also, let me give you another example. So let's also discuss the difference between a subset and a subarray. Okay, so every subarray is also a subset. So if I talk about this string, so if I give you example of a subset, then ABC is a subset, AB is a subset, BC is a subset, even AC is a subset. That means a subset can contain non-continuous parts of the array, but a subarray must be continuous. So if we talk about subarray, that means we can only take the continuous parts of the array. So ABC is a subarray, AB is a subarray, BC is a subarray, but AC is not a subarray. So given any a list of numbers or a set of n integers, you can have 2 raised to the power n possible subsets. Okay, that is exponential. And how many subarrays you can have? So clearly, if you have an array like this, so if you want to pick a smaller part of the array, so you need to pick two positions I and j, such that I and j lie inside the array, and you can pick these two positions in roughly nc2 ways. Okay, so that's of the n square order complexity. So that means if you solve this by finding a subarray that will run in order n square complexity. Okay, so since in the question it is given you have to find only one subset. Okay, so if you are able to find only one subarray also, then also your solution will get accepted. Okay, so instead of finding subset, we can see, okay, let's try to find out a subarray. If we can ensure that such an subarray always exists, we do not need to find the subset. That's the first point here. So this 24 points is because you can do an n square algorithm. You can find out all possible subarrays, and then you can check, okay, which subarrays have this particular property. Okay, and the third approach is something which we should do in a better complexity than the first two. Okay, so that gives you 39 points more. So here n is 10 raised to the power 5. That means we cannot run an n square algorithm. Okay, we have to do something n log n, or we have to do something order of n. That's what we need to do here in this case. Also, we may have some number of test cases as well. Okay, and the constraint for the test cases is not given. So let's assume we will try to do it in the best complexity that we can. Okay, so let me give you one example here. So in this example, you are given there is a single test case, there are 3 elements, and these are the elements of the set, and you have to pick a subset. You have to tell the size. So clearly this is the subset such that sum of elements of the subset, that is 6, is divisible by 3. So we have the index of the elements of the subset. So we have only one element, so its index is 2. So it's indexed from 1. This array is indexed from 1. So this is about the sample input output. Okay, so let's try to come up with something interesting that will help us to solve this problem. Okay, so let's say you have an array like this. Let's say you have 1 2 3 5, and let's say call it as 6, and let's say you have 3 here. Okay, or let's say 7 here. Okay, let's say this is the array you have, and I want to find out a sub array. Okay, so we will first ensure that if we are able to get a sub array, then our work is done. We do not need to go to the subset. That's what I am trying to say here. Okay, so in sub array, either I should get an element whose sum is directly divisible by size of the array. So here size of the array is n, that is equal to 5. And basically, if you want to find a sub array, okay, let's say this is the sub array. Okay, and you want to find out the sum of the elements of the sub array. So an efficient approach would be you first store the cumulative sum of the elements. Okay, so if you know the sum till this particular point, and if you know the sum till this particular point, then you can just find out this sum in order 1 time. Okay, so that would require a pre-processing of order n, and let's say this sum is a. So you can say, okay, sum of this part of the array is nothing but b minus a, and what we want, this sum modulo n should be equal to 0. So this implies b mod n should be equal to a mod n. Okay, so where b and a are cumulative sums of two parts of the array starting from index 0. So let us find the cumulative sum. So let's see what is the sum of the array till the first index. So this is 1, this sum is 3, this sum is 6, and this sum is 3 plus 6, that is sorry, 6 plus 6, that is 12, and let's say this sum is 19. Okay, and also I'm saying if we do mod n, so we will get sums in the range 0 to n minus 1. Okay, so this is b mod n, that means sum up to a particular point, and we are doing a mod with n similar with a. Okay, so b and a can be any positions in the array. Okay, so 1 mod 5 is 1, 3 mod 5 is 3, 6 mod 5 is 1, 12 mod 5 is 2, and 19 mod 5 is 4. Okay, so now you can see that if we're looking for two positions where we have b mod n equal to a mod n, so if I just call this part as a and if I call this part as b, okay, so at this particular point you can see we have 1 and we have 1. So at these two places we have b mod n equal to a mod n. So we have, let's call some till this particular point as b. Okay, so if I subtract a from b, what I will get? I will get this part of the array. So that is 3 plus 2, it is 5. So 3 plus 2, 5, mod 5 is actually 0. So that means we are able to get a subarray. And now my claim is such an subarray will always exist. Such a subarray will always exist. So I will try to prove my claim using pigeonhole principle. Okay, so what I do, so now I know I have 5 numbers. Okay, and these numbers can occur in the range from 0, 1, 2, 3 and 4, because we are doing mod with n. Okay, so that means if n is 5, so something mod 5 will be in the range 0 to 4. That's what my claim is, and it's true. Okay, so what I can say is okay, we have 5 numbers and we have 5 buckets. Okay, so what can happen in the worst case is that every number, or you can say best case, every number will be assigned to every bucket. Okay, so let's say you have a number in the 0th bucket, you have a number in the first bucket, you have a number in the second bucket, you have a number in the third bucket, or you will have number in the fourth bucket. So this is one possibility. But in our case, we do not have any number in the 0th bucket. Okay, so let's just ignore this particular bucket. Okay, we do not have a number in the 0th bucket, and remember 0 is a very special bucket. So if you get something of this form, b mod n equals to 0, that means you already have found a subarray where you're getting sum of elements of that subarray starting from index 0 till this particular index, doing a mod with n, that gives you 0. I will show you a case. So as of now, just leave the 0th bucket, because if you find any such sum that doing a mod with n gives you 0, your problem is already solved. Okay, so let's consider two cases where we have numbers in the range, let's say where we have numbers in the range 1 to 4, and another possibility is where we have numbers in the range 0 to 4. Okay, so that's what I'm saying. So in this particular example, you can see we have numbers in the range 1 to 4. Okay, that is what. So how many numbers we have? We have actually 5 numbers. Okay, and how many buckets we have? We have 1, 2, 3 and 4. So clearly we can say if we have 5 numbers and they need to be mapped to 4 buckets, at least 2 numbers will lie in the same bucket. That's what I'm saying here. Okay, so at least 2 numbers will lie in the same bucket. So that means if I just check how many numbers lie in the first bucket, so I have 1 that goes here. Okay, I have 3 that goes here, I have another one that goes here, I have 2 that goes here, I have 4 that goes here. Okay, so if I now check at what indices these numbers are present. Okay, so the number is present at the 0th index and another one is present at the second index. So that means the subarray that lies between the index 0 to 2 excluding index 0, that means this particular subarray, that's index 1 and 2, is of this form. So this part is B, this part is actually A, okay, and you can see the numbers are 1, 2 and 3. So we have 1, we have 2 and we have 3, and you can see this part of the array is actually divisible by 5. So according to pigeonhole principle, I can say in the first case I have 5 numbers which are lying in 4 buckets. That means at least one bucket will have two same numbers, and my goal was to find out two values where we have b mod n equal to a mod n. So according to pigeonhole, we can say such a pair will always exist in the first case. Now let us discuss what will happen in the second case. A second case is the case where we have numbers, we have 5 numbers, and let us say these numbers are lying in the range 0 to 4. Okay, so now we have 5 buckets. Okay, 0, 1, 2, 3, 4. So what I am saying is either they will lie, one number will lie in each bucket, okay, or if one of the numbers does not lie in the 0th bucket, it will lie in some other bucket. Okay, so if it lies in some other bucket 0, 1, 2, 3, 4, that also solves my problem. That means that is the basically the first case. Now if the number lies in the 0th bucket, that means we now know a subarray such that b mod n or some mod n is already 0. So let me give you another example. For example, if you have something of this form, you have, let's say, 7, 7, 7, 7 and let's say 5. So if you find out the cumulative sum of this particular array, okay, so it's 7, 14, 21, 28 and we have 33. Okay, so now what will happen in this case, or let's make it as 15, let's say it's 43 now. So if you do mod with 5, so what you get 2, you get 4, you get 1, you get 3, and here also what you get is yeah, it's 3 only. Okay, so let me say this number is, let's say, 12. Okay, so here also you will have two numbers that are lying in the same bucket, but I'm trying to make a case where this is a multiple of 5. So let's say okay, let me this is, let's say this number is 12. Okay, this is not there. Now if you see, if I just sum it up, I will get 40 and this will be 0. Okay, so now you can see there are numbers which are lying in the range 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, sorry. Now there are 5 numbers and they are equally distributed in each of these buckets. Okay, so we can say no two numbers lie in the same bucket, but there is one number which lies in the 0th bucket. So that means if there is a number that lies in the 0th bucket, so that means that particular sum mod n is already 0. Okay, so that means we have found one subarray starting from this particular index till this particular index. If I just do sum of all elements of this array, okay, so this is 28 plus 12, that is 40. 40 mod 5 is already 0. So I can just output there is a subarray that starts from index 0 and it has size of 1, 2, 3, 4, 5. So I can just throw this as an output and it will get accepted. Now you can see this is actually an order n algorithm. Okay, and I hope now it is clear. Now both the cases are clear. So what we did according to pigeonhole was that either the numbers will lie in the buckets 1 to 4. Okay, so no sum is directly so either these will lie in the range 0 to 4 or they will lie in the range 1 to 4. If they lie in the range 1 to 4, then there will be at least two numbers that will be mapped to the same bucket. So answer will be yes in this case. And if they're not mapped from 1 to 4, they will be mapped from 0 to 4, and if there is a single number that lies in the zeroth bucket, then also we can say we found out a possible sub array or a subset that sum mod that follows this property, sum mod n is equal to 0. Okay, so the coding part I am leaving up to you. You can use something of this frequency kind of an array to maintain, and you can just solve it on your own. Okay, so remember, it will never give a case where the answer will be -1. You will always find a subset. Hi everyone. So in this video, we will discuss a problem called gray similar code from CodeChef, and it's given that it's a special type of code in which two adjacent numbers have exactly one different digit in their binary representation. Okay, maybe let's say the first number is like this, and let's say the second number might be like this. So you can see two adjacent numbers have exactly one bit different in the representation. Okay, maybe the next number is like this. So again, you can see there is only one bit of difference between these two numbers, and let's say the next is something like this. So again, we have a difference of just one bit. So it says we are given lot of numbers. Okay, so we are given n non-negative integers in the sequence 1 to n, and every two adjacent numbers have, and these are 64-bit integers. Okay, so you can see a of I is less than 2 raised to the power 64. That means at most 64 bits are needed to store any number. Okay, and also your task is to check whether there exist four numbers a1, a2, a3, a4 such that if you do XOR of all four numbers, such that you do a1 XOR, a2 XOR, a3 XOR, a4, this XOR turns out to be 0. Okay, so you have to check yes or no. Okay, that's what you need to do. And let's see the value of n. Now you can see this n is actually a very large number. Okay, so this is 10 power 5. Okay, and you cannot do brute force. You cannot run order of n4 complexity in which you try to pick every number and you try to generate all possible combinations of these four numbers. Okay, so this is something that is not acceptable here. So we have to output yes or we have to output no, if it is possible or not possible. Okay, now you have to think how we can actually solve this problem. So let us carefully analyze the situation. So a careful analysis will give us a hint that all of them are 64-bit numbers. Okay, so we have 64-bit numbers. That means if I just make a representation here, you can have 64 places. Okay, and also one property that we can exploit here is that these numbers are gray codes. Okay, they are very special numbers. So let's say this is a number, and you know the next number will differ with only one bit. Maybe that next number is 11001. Now if you do a XOR of these two numbers, okay, so I'm just taking, let's say this number is ai, this number is a of I plus 1. So if you do a XOR, what you will get? You will get 0, 0, 1 and 0. Okay, so since these numbers differ at only one position, okay, so XOR of two consecutive numbers will give us a number in which you will have only one set bit. Okay, you will always have a one set bit. So what I do, let's say I have numbers from a1, a2, a3, a4 and so on. Okay, so if I do a XOR of these numbers, I will get number of this form. Maybe I will get a um, I will get a set bit at one of those positions. Okay, and similarly, let's say I do it till only 130. You will come to know why I'm doing it till only 130. So if number of numbers is, let's say, more than let's say n is 10 power 5. Okay, but let's say I just see the first 130 numbers, let's say, and I do a XOR of every two pairs of numbers, so that will actually give me 65 pairs. Okay, so I will get 65 pairs in which you will have set bit at only 64 unique positions. Okay, so maybe now if it is a 64-bit number and doing a XOR of two numbers will give me a number with only one set bit. That means in these 65 pairs I will have at least two numbers in which one bit is on the same position. Okay, so that means at least at least two such pairs exists. Let's call them as, let's say, ax plus 1 and ay plus 1. So these two pairs are such that if I do XOR of all of them, they will give me a zero answer. So I hope you are agreeing to this statement, because doing a XOR of 130 numbers, okay, let's say if n is greater than equal to 130, so if I do a XOR of first 130 numbers, then there will be 65 pairs in which there can be only 64 positions of set bits. Okay, and all other bits are zeros, so that means two pairs have the set bit in the exactly same position, and if I do a XOR of those pairs, it will give me a zero answer. So this is how we have applied pigeonhole principle in this example. Now the question is, okay, so that means my answer will be always yes if in the question the value of n is given as greater than equal to 130. So no need to read the array, no need to scan the integers, you can directly output yes if n is greater than equal to 130. But suppose if n is, let's say, 100, or let's say n is less than 130, what you will do? So in such a case, what you can do is, you can okay, let's see what is the value of n here. Yes, so whatever is the value of n, okay, so it doesn't matter. So if n is less than let's say 130, so n is of the order, let's say, 100, in that case you can also apply a brute force search. Okay, so in brute force, what you can do, you can pick the first number using a for loop, another for loop to pick the second number, another for loop to pick the third number, and let's say it picks a number a, it picks a number b, it picks a number c, and now you want to look for a number d. Okay, so what you can do, you can say, okay, I want something of this form: a's or b's or c's or d should be equal to 0. So that means d should be equal to a's or b's or c. So what you can do, to find out the fourth number, you can do a search operation. Okay, so that search can be a binary search if you sort all of these numbers in n log n time, or you can maintain a hash map. Okay, so that means if you run 3 for loops, that will take order of n cube time, and since n is of the order 100, it will take 10 per 6, and if you run binary search, that will be n cube into log n. Okay, so n cube into log n, and that can be done. Okay, so this complexity will pass for the case when n is less than equal to 130. Okay, or when n is less than 130. So for n equal less than 130, you can just do brute force, and if n is greater than equal to 130, you can just output yes, because of the pigeonhole principle. So I hope this question is clear, and you will be able to submit it now on CodeChef. Hi everyone, so now we will discuss very interesting problem from Spoj. It's called Holi, or Holiday Accommodation and Sort. It's a problem from ACM ICPC regional contest, and let's go through the problem statement line by line. So it says people have many ways to save money on accommodation when they're on vacation, blah blah. One of these ways is exchanging houses with these people. Okay, so there are some people who want to exchange houses when they go on vacation. So there is a group of n people who want to travel around the world. They live in different cities, so they can travel to some other people's city. Okay, so people want to move from one city to another and use a temporary house, and they want to make a plan and choose a destination for each person. Okay, so there are two rules which need to be satisfied. All the people should go to one of the other people's city. That means no one is going to stay at home, and two of them never go to the same city. Okay, that means a single traveler will go to another city, and no other traveler will come to that city because they are not willing to share house. You can assume that a single city has a single house. They also want to maximize the sum of all people's travel distance. Okay, so they want to travel a lot, and they want that the total distance they travel by plane or through road is maximized. Okay, the travel distance of a person is the distance between the city in which he lives and city he travels to. Okay, for example, a person lives in Delhi and he travels to New York, so the distance between these two cities is the travel distance. Okay, given the highways information, it's your job to find out the best plan and maximum total travel distance of all people. So you have to maximize the total travel distance of all the people combined. Okay, now let us see the input. The first line of the input gives us one integer t, indicating the number of test cases. Each test case contains an integer n, representing the number of cities. Okay, so that means these many nodes are there, or these many nodes are there in the network. Okay, the following n minus 1 lines contains three integer x, y, z. Okay, so that means there is an highway between x and city y, and z denotes the length of that particular highway, and you can assume the highways are connected and bidirectional. So it's a graph problem in which you have direct bidirectional edges. Also, it's given all of the cities are connected, only then you can connect from one city to another. Okay, and it's also given there are n minus 1 edges. So this is a very important hint. So a graph in which a connected graph in which you have n nodes and you have n minus 1 edges is actually a tree. Okay, so this is actually a tree, and it's a weighted tree. Okay, so maybe this is y1, this is y2, this is z1, this is z2. So it's going to be a weighted tree. Okay, so that means no cycle is present in the graph. For each test case, we have to print the largest total distance traveled by all the people. That's what we have to print. Okay, so this is what it is given to us. So let us see. Let's see the first test case. Okay, also there is also something given: the travelers always choose the shortest path while traveling. So I will explain you what this statement means. Yes, so let's see one example here. So it is given that there are four cities. So let's number the cities as 1, 2, 3, and 4. From 1 to 2, there is a distance of 3 units. From 2 to 3, there is a distance of 2 units. And from 3 to 4, there is a distance of 2 unit. And what you need to do now, you need to maximize the total distance traveled by these four persons. Okay, so there are four persons, and we have to maximize the total distance. Okay, so let me just name these nodes as A, B, C, and D. Okay, and this is 3, 2, 2. So what one thing I can do is there can be lot of possibilities. Okay, so if I just swap A with B and C with D, so how much travel I will have? So if we swap these two, it will be 3 plus 3, 6. And if I swap C and D, it will be 2 plus 2, that is 4. So you can see in this case the total distance traveled is 10 unit, but this is not an optimal solution. So what you can do is you can actually exchange 1 with, let's say, 3, and you can exchange 2 with 4. In that case, what you can do is 1 and 3 will travel a total distance of 3 plus 2, 5 plus 5, 10. So if you exchange 1 with 3, so that will contribute a distance of 10. And if you exchange 4 with 2, that will contribute a total distance of 2 plus 2, 4 plus 4, that's 8. Okay, so this is 10 plus 8, that is 18 units. And also you can see yourself, if you exchange 1 with 4 and you exchange 2 with 3, that will also contribute a total distance of 3 plus 2 plus 2, that is 14, and this will contribute a distance of 4, so it will be 18 units. Okay, so in the best case, the maximum distance we can get is 18 units, and we want to maximize the total distance under the condition that the travelers take the shortest path to reach their destination. Okay, so what does this line mean? So this line basically means if 4 has to travel to 2, it will take the shortest path to reach 2, that is this path, and it will not do something like this, that it first goes to 1 and then it comes back to 2. Okay, so it will not take a path like this, so it will take the shortest path to reach 2. That's another clarification that I have to give from the question. Okay, so now you have understood the sample input output. Now let us discuss how we can proceed with the solution. Okay, so let's discuss, let's make a sample tree. Maybe we have a tree like this, which is actually a graph. Okay, maybe this is the set of nodes, and let's talk about what we can do. Okay, so what we can actually do now. So one way is you can generate all possible combinations of persons visiting in all other nodes. Okay, for example, if the persons are like this, 1 2 3 4, you can generate n factorial possibilities, and for every possibility you can try to compute what is the distance traveled by each person, and you can uh, sum up that particular distance for all the persons. Okay, so this complexity would be very bad. It will turn out to be an exponential complexity, since n is a large number. I think it's of the order 10 per 5 or 6. Then this type of an approach will definitely fail. Okay, so another approach is we are actually not interested in finding out where a particular person X will be located after the final migration happens. So what we are interested in finding is what is the maximum distance that will be traveled by all the persons. Okay, so we can kind of include a greedy thinking here. In order to maximize the total distance, we can say, okay, we will try to maximize the distance that is traveled through every edge. Okay, so maximize the distance through every possible edge. Okay, so through every edge, so that's what we need to do. So if we are able to maximize the distance through every edge, we will be able to solve this particular problem. Now you may say, okay, let's see how we can maximize the distance through every edge. So let us try to break this graph about this edge from, let's say, x to y. Let's say there is an edge from x to y, and I'm interested in finding out how many people will actually travel through this edge. Okay, so for that we need to know the number of people in this part of the graph. So that's 1 2 3 4 5 6, and I also need to know the number of people in this part of the graph, and maybe let's say this is 7 and this is 8. Okay, so let's try to find out what is the number of people in this part of the graph. So that is 1 2 3 4 5 6 7. Okay, so we have 7 people in this graph. Maybe let's add one more. Let's add one more, and let's say this person is 8. So we have 1 2 3 4 5 6 7 and 8. Now this right hand side graph has 8 people, and the left hand side component of the graph has 6 people. So what do you think, how many people can travel in the worst case or in the best case through this edge? Okay, so let's say We have 6 people here, we have 8 people here. Now obviously, uh, to in order to maximize the total travel through this edge, what I can do is I can pick any 6 persons from the right hand side part and send them across to the other part. Okay, and I can pick 6 persons, that is all of the persons in this part of the graph, and send them to this part. So that is how this utilization of edge will be maximum. Okay, so that means the total persons that can travel is minimum of 6 comma 8 into 2, because the movement is going to happen across both sides. So this edge will be used 12 times. Okay, and what will be the contribution of this edge to the total distance traveled? It will be 12 times the weight of the edge. Okay, let's say that weight edge is z, so it will be 12 times of z. So this is the contribution of this edge in this uh, movement. Okay, so you cannot use this edge more than these many times, and by doing such a phenomenon on every edge, we can ensure that we are able to find out the total maximum distance by summing this up through every edge. Okay, now you may ask, okay, how do we compute this now? Okay, so for that, one possible idea is you break the graph at every edge. Okay, you will get two components of the graph. Okay, you will get two components of the graph, and from for those two components you can find out what is the number of nodes in the left part, let's say n of x, and what is the number of nodes in the right part, let's say n of y. So you use a traversal such as BFS or DFS to find out the number of members in the number of nodes in that particular part of the graph. Okay, so from this can be done in linear time, and from that you can find out minimum of nx and ny, and you can say, okay, 2 into the weight of that particular edge. Okay, so that will kind of give you an idea, and you will get a sub problem which you can solve recursively, and so on. So but this again will be a very complex method, because if you break this graph about this particular edge, okay, then you have e number of edges, and if you do BFS and DFS every time, that will take linear time, that will take order of v plus time, so you will end up getting this quadratic complexity. Okay, so that may also not pass. So we have to come up with something better. Okay, so we have to, now we will make another attempt in which we will try to do it in just linear time. So the idea will remain same. Okay, so idea will be that we will try to break the graph about every edge, and let me just take the sample test case that we have. Okay, and we will assume, let's say this is A, this is B, this is C, and this is D. This is 1, this, I think this was 3, this was 2, and this is also 2. So what I can do is I can actually do it in just a single DFS traversal. Okay, so what I can do is I can say, okay, let me give you another diagram as well. Okay, now suppose, let's say this is your graph, suppose. Okay, so what do, you start doing, let's say, DFS from this particular node. Okay, and you make a call on this particular node. Okay, so that is a small component of the graph, and you ask this component what is your size, how many nodes you have in this component. Okay, so this component says, okay, it starts a DFS from this node, it says my count is 1, it makes a call on its child, this says my count is 1, so it returns this count to the parent. So this parent count becomes 1 plus 1 2, and parent makes another call to this node, it says, okay, my count is also 1, so parent says, okay, my count is 3. So this is how we know this component size is 3, and now this size 3 is returned to this parent node. Okay, now we are interested in finding out what is the total number of nodes in this part of the graph. Okay, so for that, what we can say is, we know in total we have n number of nodes. So if one of the child says, okay, there are 3 nodes, the other part of the graph will have n minus 3 nodes. And how many times this edge will be used? That will be minimum of 3 comma n minus 3. Okay, so this is how you can find out, okay, what is the number of nodes, number of people that will cross this edge. So that will be into 2, and total cost will be into weight. Okay, so when you do DFS, you will do one thing: you will always return the size of the subgraph or size of the component from which you are returning back. Okay, so for example, let's try to make a DFS call from A. Okay, and DFS will say, okay, at this point my count is 1 and I want to count how many nodes I have in my entire graph. So A makes a call on B and B starts another DFS call. So B says, okay, I initialize my count with 1 and I will make a call on C, on my children, on my neighbors. And C says, okay, let me say my count is 1 and I will make call on any children I have. So C makes a call on D. So D says, okay, my count is 1 and I will make a call on any children I have. So since D has no children, so it return back to C and it says, okay, my count is 1. So C comes to know that this D there is one component in the graph, so this count becomes 2. Now what happens at this place is, when C is making a call on D, we are basically talking about utilization through this edge. Okay, so you can treat it like this: we are at A, B, C. Okay, and we have, let's say, broken the graph about this edge, and C made a call on D and D returned. So let's say D is a component and D returns a 1. So C comes to know that on the right hand side of this edge, on the left hand side of this edge, the graph has one node only, and in this particular left hand side graph there would be n minus 1, that is 4 minus 1, 3 nodes. So how many people will cross this edge in the worst case? That will be minimum of 1 and 3. Okay, so we know that finally there is one person who will occupy node D. So that person can be one of these A, B and C. We do not know. So whatever it is, so we will say that will be multiplied by 2 into the weight of edge, that is 2. So that means the total contribution of this edge will be 4. Okay, so that's fine. Now we come back to C. Okay, and C will return some information to its parent. So this information is the count of the number of nodes in the graph of C. Now we are at this particular edge. Okay, so we have already traversed this edge, this part of the graph, and C is now going to return to its parent. So now B will come to know, okay, C is saying I have two components in my I have 2 nodes in my graph. So B knows, okay, there are 4 minus 2, that there are 2 nodes in the graph. Okay, so that means how many people will travel through this edge from B to C. Okay, so it will be minimum of 2 comma 2, and that makes sense. So that means 2 people will travel. So that means in the combinations we have seen, both A and B should come to this part of the graph and C and D should move to the topmost part of the graph. So total movement will be minimum of 2 comma 2 into 2 into the weight of the edge. So it is 2 into 2 into 2, that is 8 units. Okay, so the first edge is contributing 4 units, the next edge is contributing 8 units. Now let us come back here. Okay, so B now knows count is 1 and also the count of children of B is 2. So now B knows there are 3 nodes present in the graph that starts from B. So let's say from A to B. Let's talk about this edge now. We have B, C and D. So now the graph is broken about this edge. Okay, we are actually not breaking it, but we are just counting it down. So when you make a call from A to B, okay, or when you return from B to A, let's say, so B tells A there are 3 components in my subgraph. Okay, and A will know, okay, so out of total 4 nodes, 3 are present in the other part. So in this part A, there is only 1 node. Okay, so it will be minimum of 1 comma 3. The number of people traversing through this edge will be minimum of 1 comma 3 into 2 into weight of the edge, that is 3. So this contribution will be 6 units. Okay, now if you add up the total contribution, that is 4 plus 8 plus 6, so this turns out to be 18 units, and this is the maximum contribution that is possible. So now you can see we actually have used pigeonhole principle at this particular point. So we are breaking the graph into two parts. The one part has x nodes, the other part has y nodes, and in order to figure out how many people will travel through this edge, we actually used pigeonhole, because we said if x is smaller, then at most x pigeons will travel from y part to x part, or if y is smaller, we will say at most y pigeons will travel from x part to y part. And this is nothing but a example of pigeonhole principle. So I hope you got an idea how we can solve this problem using DFS, and the overall complexity of this will be order of v plus e, that is the complexity of DFS. Okay, and now we will see the implementation of same in the next video. So thanks a lot. See you guys. Hi everyone. Now let's implement the problem wholly from Spoj. So I am constructing a graph. Okay, so that will have the number of vertices, and it will have an adjacency list. So let's construct that, and let's construct a graph constructor that will get the number of vertices, and we can just put it like this, and we can say L equals to new list, and it is a list of pair intent V. So since this is a weighted graph, okay, it's a weighted tree, so I need two things. One, to, so suppose there is an edge from x to y and with weight of z, so I will say, okay, in the adjacency list of x put y comma z, and also in the adjacency list of y put x comma z. Okay, so where z is the weight, and this is the source, and this is the destination. Okay, so this is how I am going to make a adjacency list, and we are making a array of lists with so there are v linked lists. Okay, so it's an array of v linked lists. Okay, so this is L of 0, this is L of 1, and similarly we have L of v minus 1. So we have these many linked lists in the graph. Now what we need to do, we need to define a function called add edge. So let's say there is an edge from u to v, and there is a cost associated. So what I can do, we can say L of u dot pushback v, and I can say L of v dot pushback u, since it is a bidirectional graph. So that's the add edge function. Now we need to write the main DFS function which will help us to do the work. Okay, so let's see. So I think int DFS is the function, and we will maintain a visited array so that we do not traverse any node again. So we can say bool star visited equals new bool v of 0, and we will also maintain a count array that will actually help us to store the count of every node. Okay, so that we are going to maintain. So new int of v of 0. Okay, so this kind of an initialization does not work in my Sublime, so I can just put a for loop and set all these values as 0. So for int I equals to 0, I less than v, I plus plus, and I can say visited of I equals to false, and count of I equals to 0. So initially count of every node is 0, or you can also put it as 1, that's totally your choice. And here I can say, okay, as I go through my DFS calls, I will maintain my answer. Okay, so answer denotes the total distance traveled. So we will make a helper function that will get the source node. Source can be any node, let's say it's the 0th node. Then we have the visited array, and then we have the count array, and then we have the answer. So I'm going to update answer by reference. Okay, so let's return answer here. Okay, and let's make a function called DFS helper. Okay, so int DFS helper, and here we can get the node at which we are currently present, and we can get the visited array, and we can get the count array, and we can get the answer. Now you can see there are actually two things that you need to do while returning from a node. Okay, for example, from A you made a call on B made a call on C, and C made a call on D. Okay, so D returns something to C returns something to B, and B will return something to A. So that something is nothing but the count of nodes. Okay, so that is what this int data type tells me. So int basically denotes the count of the subgraph starting from that node from which we are returning back to the parent node. So at this particular point, when B returns to A, this count will be 3. Okay, and the total distance traveled and will be updated by reference, because we are already returning the count, so we cannot return the total distance either unless we make a pair of intent. Okay, so either we do that or we can just pass this variable by reference. Now let's see what we need to do. So as soon as you come to a node, what do? You mark that node as visited. So that's what you do in DFS. Mark the node as visited, and you can say visited of that particular node. This is equal to true, and also set the count of that particular node as 1. So count of that node is going to be 1. That's what you can do. And here you can say for auto, let's go to every neighbor of that particular node. Okay, so neighbor will be a pair. So neighbor pair that's there in L of node. We can first find out the name of the node. Okay, so int neighbor, that is going to be neighbor pair dot first. Okay, so there is small thing that I missed here, so it should be equal to make pair, and here I can say v comma cost. Okay, and it should be make pair, and I can say u comma cost. Okay, so that's how we can say the first element of this pair is the node, and the second element is the cost. So here we can check if that particular neighbor is not visited. If not visited neighbor, we will try to visit that particular neighbor. Okay, so that we can do recursively. So okay, let me just explain you what we are going to do here is. So let's say from A you find a neighbor B that is not visited, so you make a recursive call on this neighbor, and once that call is over, this recursive call will return me the count of that particular node. Okay, so the count of children and the count of this, so it will be 1 plus count of its children, okay, and grandchildren and so on. So it will be the total size of this particular graph, that is 3. So that 3 should be added to the size of A, because it is also possible that someone else might have called A and A had lot of branches. Then you need to sum up all of them into A. Okay, so you can see count of the parent, that is A, so that is count of node, should be incremented by a particular value. Okay, so that value is nothing but DFS helper. You make a call on one of its children, and that children returns whatever is the whatever count that children returns should be added to the count of parent. So here you can say it's V, this should be neighbor, and we should have visited, and we should have count, and we should have answer. So that will basically increment the count of A by this particular factor. Okay, so A made a call on B, and recursively DFS happened on this particular tree, and B returned, okay, my count is 3. You have to do one more thing. You have to increment the contribution of this edge to the answer, because you made a call on A, and once this call is over, you are coming back from B to A. Okay, so at this particular step, you have already visited the entire subtree of B recursively. So what you need to do is you need to increment your answer. Okay, so I can say answer will be incremented by twice of minimum of x and y. Okay, so let's compute the number of nodes in one part of the array, nx, and let's compute the number of nodes in the other part of the array. So nx will be nothing but count of that neighbor. Okay, So in one part of the array it will be count of that particular neighbor, and the other part of the array it will be v minus nx. Okay, and here you can say nx and ny. Okay, so carefully see, it is the count of neighbor, it's not the count of node. Okay, so a has a neighbor b, and b, once the DFS call on b is complete, then we have count of b that is set as 3. Okay, so we will update it, and once all the calls are over, okay, so once all the neighbors have been visited of for b, we will update this count as 3. Okay, so now b returns 3 here, so that's the count of neighbor. Okay, so since this neighbor is already visited, so its count is already updated. So n of y is the other part, this part, so it is 4 minus 3, that is 1, multiplied by the weight of the edge. Okay, so a to b we have an edge, so whose weight is given here, so that weight is neighbor pair dot second. Okay, so you multiply this with the weight. Okay, and that's it, that will increment your answer. And finally, just before just before leaving the node a, okay, or the parent node, what do you need to do? You need to return the count of this particular parent to the parent of this node. Okay, so once you are leaving from a node, okay, once you are going back from a node, you return the count of that particular node. Okay, so that that count is nothing but return count of the node, that's it. Okay, so this is the DFS helper function, and that's it. Okay, so you will see it will run in order of, okay, so it will run in order of n times. So now I have made the graph, and let's try to run our code. Okay, and you can see we are getting 18 as the answer for this particular graph. So if even some of the things are little unclear, I can just dry run it, and so that you feel more comfortable in the implementation. Okay, so what I do, I maintain a visited array that you already know. We have a visited array for 4 nodes, and we have a count array that is also there for all the 4 nodes, 0 1 2 3, and initially all the counts are 0, and we start the DFS from the 0th node, from this particular node, and we say okay, find a neighbor that's there. So 0 finds a neighbor 1, and from 1 we again initiate another recursive call. So at 1 we say okay, count of this node is actually 1, so we mark this node as visited, and we say okay, 0 has a count 1. So from there we go to a neighbor that's 1, and we say okay, this count is 1, and we mark this node 1 as visited, and we say okay, this count is 1. And from 1 we go to another node that's a neighbor of 1, that's 2, we say okay, this has a count of 1, and we mark this node as visited also. Okay, so this is the visited array, and this is the count array. So from 2 we go to a node 3, and we say okay, 3 is visited and count of 3 is 1. And from 3 we can see this for loop will not go to any other node, so it will just return the count of node. So it says 3 returns a count of 1 to 2, but so now you are in this call, so you are in this function where 2 had made a call to 3. Okay, so 2 had made a call to 3, so the neighbor was 3 and the node was 2. So at this particular point, you know, the count of neighbor, so count of 3 is 1, so n of x is 1, and n of y becomes 3. So in your answer you add the contribution of this edge. Okay, so this edge has a contribution of 2 into minimum of 1 and 3, that's 1, into the weight of the edge, so that is 2. So this contribution is 2 into 2, 4. Okay, so this gets added to your answer. So answer which was initially 0, now the answer is 0 plus 4. Okay, and also at this particular point you also update the count of node by this particular factor. So count of 2 is updated by 1 plus 1, so this count becomes 2. Now in 2 you cannot find a neighbor which is not visited, so the only option is you have to go back to 1. Okay, so you return something to 1, so that count is 2, And one now knows, okay, when you're making a call to its neighbor, now node is 1 and the neighbor is 2. Okay. And also one knows that you're returning some information here, so that information is count of this 2, that is equal to 2. So you increment the count of node 1 by a factor of 2, so this count becomes actually 3. And also you know the value of nx, so this nx is 2, and n of y, this is also 2. So you add this value to your answer, so this value is nothing but 2 into 2 into 2, so this value is 8. So your answer is incremented by 8. And finally you are back in this function call where 0 had made a call to 1, and 1 will return 3 to 0. Okay, so in this case your node is 0 and your neighbor is 1, and count of neighbor is 3, and the value of nx is 3, value of ny is 1. So it will be 2 into minimum of 1 and 3, that's 1 into the edge weight. So it is, this value is nothing but 6. Okay, so you add 6 to your answer and you return count of node. Okay, so to this function here you basically get the size of the entire tree. So this function actually returns a value 4, but we are returning answer from this function, so that answer is nothing but 18. So I hope this one is now clear and you will be able to apply DFS to more such graphs like these. Hi everyone. So now we are going to discuss a concept that is called mathematical expectation. So we will discuss what is expectation. So let's start. So expectation is some kind of an average value of a random variable. Okay, so it's like an average value of an random variable. Okay, now you may ask, what is a random variable? So a random variable is like an outcome of an experiment. Okay, for example, uh, you throw a dice. Okay, you can end up getting a random number between 1 to 6. Okay, so let's say you throw a die, and what outcome you will get, that's actually pretty random. So let's say x denotes a random variable, and that denotes the outcome of a dice throw. Okay, so in x you can have the values between 1 2 3 4 5 6, and in this case you can see x is a discrete random variable. Okay, and you may have some event where this x can be continuous. Okay, for example, maybe you want to predict the weather for the next day. Okay, so it can be a range maybe from 20 degrees to let's say 50 degrees. Okay, and then you can have values like 20.1 or 20.25 degrees Celsius. So in this case x is a random variable. Okay, and with each outcome there would be a associated probability. For example, let's say if it is a summer season, then if I denote x along this axis, and it is expected that the average temperature remains around 40 degrees Celsius. Okay, so then what you can say is maybe this kind of a probability distribution you may have for x. Okay, so in this case x is a continuous variable, and you will see this kind of a probability distribution. Okay, so there is a higher probability of temperature being around 40 degree, and there is a lower probability of temperature being around 0 degree, and there is again a lower probability of temperature being around 60 degrees Celsius. So in this case you have a probability distribution function, but in case of a discrete variable you will have some probabilities for everything. Okay, so let's say x is 1, when x is 2 3 4 5 6, so you will have the same probability. Okay, so this probability will be nothing but 1 by 6, because if a fair dice is thrown, the probability of getting every number is 1 by 6. So basically we will define the average value of a random variable using expectation. So now let's define how this value can be mathematically defined. Okay, so expectation of a random variable x can be written as summation over all I x of I into p of xi. Okay, so this is the case when x is a discrete variable. Okay, so the first case, and there is a second case when x is a random variable. So let us try to put this formula into our example. So it basically says it is the value of xi multiplied by the probability of xi and summationed over all possible values that x can get. So in case of our dice throw experiment, the expected value of a dice throw, let's see what it comes out to be. So this value comes out to be 1 by 6 into 1 plus 1 by 6 into 2 plus 1 by 6 into 3 plus 1 by 6 into 4 plus 1 by 6 into 5 plus 1 by 6 into 6. Okay, so if you just take 1 by 6 common, it turns out to be 1 plus 2 plus 3 plus 4 plus 5 plus 6. Now you can see this is equal to 3.5. Now this is some sort of an average value that you can expect when you throw a dice. Okay, and this is not equal to the most probable value. Okay, so this is not what you are most likely to get, because 3.5 cannot directly occur on the die, but this is kind of an average value that you can expect over a long period of dice throws. So this is what expectation means. Now let's see the expectation formula for the case when you have continuous distribution. So in this case you can say expectation of the random variable x can be written as integration over x into p of x dx. Okay, so this is again nothing but the area under the curve. Okay, and this is actually same as this. Here we are using a summation sign and here we are using a integration. So this is how you can calculate expectation for a continuous variable. Okay, but for our case this is very unlikely that you will get a continuous variable in a competitive programming problem, but this may be useful in maths and statistics and machine learning and so on. Okay, so this is what expectation is, and in the coming videos we will see some examples and that will make the things more clear to you. Hi everyone. So now we will discuss one rule that's called as rule of linearity of expectation. Okay. So this rule basically says that expected value, that is denoted using E, of sum of two random variables. Okay. Sum of two random variables that I'm denoting using X and Y is basically equal to the sum of their individual expected values. Okay, so this is the individual expected value of x and y, regardless of the fact that x or y are independent or not. Okay, so expected value of sum of two random variables is equal to their sum of individual expected values. Okay, so that's what I am going saying here, individual expected values. For example, suppose I have two dice now. Okay, if we have two dice and we can throw them independently. Okay, so let's say the outcome on the first die is a random variable that's denoted using x. The outcome on the second die is denoted using y. So we want to find out what is the expected sum of numbers we can get from the two dice. Okay, so clearly what we will do is we will try to make all possible cases if we go by the basic formula. So we'll have a table. Suppose the first die throws 1, second die throws 1, so we get a sum 2. So first die throws 1, second die throws 2, we get a sum 3, and so on. Okay, so we will have a 6 by 6 grid and we'll try to find out the probability of each outcome, that is like 1 by 6 into 1 by 6 into whatever is the sum I get, and I can do the summation over all of those 36 cases. Okay, so that's one way. But if we just use this property, the rule of linearity of expectation, we can just break the problem into two parts. So we can say, okay, what is the expected value from the first die? So that we know is 3.5. What is the expected value from the second die? That we also know is 3.5. So we can just say, okay, this outcome is 7. And this is how easily we can just compute the expected value on sum of sum of two dice. Okay, so this is what is rule of linearity of expectation. Okay, so one add-on that I want to make here is sometimes you may also feel this rule is written in this form: e of ax plus by. So where a and b are constants, so this can be written as a times e of x plus b times e of y. Okay, so this might be a case sometimes where your expectation is multiplied by some constants a and b. So that what you need to do in this case. Okay, so these two are basically same, and you can also expand it for more number of variables. You can have x plus y plus z plus w and so on, and this rule will work well. Okay, so that's one thing. Another thing is, uh, in this case, when we were saying, okay, x is a random variable for first die throw and y is a random variable for second dice throw, so both x and y were independent. Okay, but the important thing about this rule is it also holds true when x and y are dependent. Okay, so let's see another case. Let's say case 2, where x and y are dependent on one another. Okay, maybe y is dependent upon x, and so, or maybe x is dependent upon y. So let me give you one example. Let's say if the sum of numbers that is rolled on two dice. Okay, let's say sum of numbers rolled on a dice is a. Okay, so this is the question. Okay, you are throwing two dice and it says sum of numbers rolled on dice. Okay, both die is a. Okay, so whatever you roll on two dice, let's say the first die gives you some x1, second die gives you some y1. The sum is denoted as a, and also their product is given by b. So x1 into y1 is given by b. So you are interested in finding out the expected value of a plus b. So what is the outcome you can get by adding this sum with this product? So one way is you again adopt the basic way. You try to find out all possibilities here and then you find out the expectation. Another is you can just use the rule of linearity of expectation. Okay, so you can just break it into ea plus eb, and remember here x and y are dependent. Okay, so your product basically also depends upon what is the sum. Okay, so if the numbers are 4 plus 3, your sum is 7, and your product will be 4 into 3 12. Okay, so here the event b or the outcome b is not independent of outcome a. Okay, so but the good thing is rule of linearity of expectation still holds true. So we know what is the expected value of a. So if two die are thrown, we know the expected sum of them is nothing but 3.5 plus 3.5. So this is e of a, that is 7, plus you can also find out what is the expected value of b. You can further break it into down into two parts. So we have uh, we can say this is nothing but 3.5 into 3.5. Okay, so this turns out to be somewhere around, it will be around 19.25. Okay, so this is what it is to be. Okay, so this is how you can use rule of linearity of expectation in some problems where it is required. Hi, so in this video, we will solve one basic problem. It says, what is the expected number of coin flips to get a head? Okay, so you are throwing a fair coin in which you can either get a head or you can get a tail. So it asks, what is the expected number of throws you should make in order to get a head? So let's assume our answer is x. We do not know, but we can assume that after throwing a coin x number of times, we will get a head. Now, when you throw a coin, you can end up getting two cases. Okay, so the first case is you get the head on the very first attempt. Okay, so that means the number of throws is 1, and the probability of getting a head is 1 by 2. Okay, okay, so this is the number of throws and this is the probability. Okay, so I'm using the formula sigma xi into pi, but it can also happen that on the very first throw you get a tail. So what will happen in this case? The probability of getting a tail is, we know it's 1 by 2, and we should also multiply it with the number of throws we will need to get an head. Okay, so after getting a tail, we will make some more throws to get ahead. Okay, we do not know how many throws will be needed, so let us assume we will need x number of throws. Okay, so the total number of throws that we took in this case is actually 1 plus x. Okay, so we have defined a recursive relation between x. So where we say, okay, if you get a head in the very first throw, so that means you will multiply 1 with the probability 1 by 2. Otherwise, if you get a tail, that means you have to make x number of more throws to expect a head. Okay, so the total number of throws is, we have one throw which got wasted, plus x number of throws are needed. Okay, and the probability of this event getting happening is 1 by 2, because that's the probability of tail also. So if you simplify this equation, you will get 2x equals to 1 plus x plus 1. Okay, so this gives you x equals to 2. So that means if you throw a fair coin 2 times, you can expect one head, and that's pretty logical as well. Okay, so that's it. Hi everyone. So in this lecture, we are going to solve one problem that is based upon mathematical expectation. Okay. So let's see what is the question. So the question is, what is the expected number of trials needed to get two consecutive heads? Okay. So you are flipping a coin and you're interested in finding out how many trials you will need to get two consecutive heads. Okay. So something like this. So if you flip a coin, you get a head. In the next flip, you also get a head. So how many total number of trials will be needed to get two consecutive heads? So let us assume the expected number of trials that we want is x, and we want to find out this value of x. Okay, so let's build the equation. So x equals to, and now we will discuss what possibilities can be there. Suppose you flip a coin and that can show you head with 1 by 2 probability, and it can also show you tail with the 1 by 2 probability. Suppose in the first throw you get a tail. Okay, so what is the probability of getting a tail? It's actually half, and you are not able to get a head. That means uh, you will have some more number of trials to get two consecutive heads. Okay, so expected number of trials that you will need to get a head will be again x. So in all, this will become x plus 1 number of tries. Okay, so we will multiply probability with the number of tries that we will need, that is x plus 1, and we have to handle other cases as well. Okay, for example, in the first throw you get a head. Okay, and you also want to get a head in the next throw as well. So in the next throw you can either end up getting a head or you can end up getting a tail. So what will happen in this case? So suppose in the first throw you get a head, and in the next throw you also get a head, and you will multiply this with the number of trials needed. So number of trials needed is 2, because in both the trials you are getting heads. So this is the case when you get a tail followed by something. This is the case when you are getting head followed by an head. And the third case it would be, in the first row you get a head, but in the next row instead of getting a head you get a tail. Okay, so this actually wastes two trials. So what is the probability of occurrence of a head followed by a tail? So clearly it is 1 by 2 into 1 by 2 into number of trials that you will need. Okay, so as we have seen in the earlier videos also, the expectation is nothing but uh, xi into p of xi. Okay, so xi is the number of tries you're needed, and p of xi is the probability of this event. Okay, so what we are going to do, so total number of trials will be in this case x plus 2, because we have wasted two trials and we would expect we will need x number of tries more to solve this. Okay, so this will be x plus 2. Okay, so now this is our equation and we would like to solve this equation. So I can say this is, let's multiply this equation by 4, so this becomes 4x. This is equal to 2 times x plus 1. This is 2 and this is x plus 2. Okay, so let's simplify this. This is 2x, that's equal to 2x plus 2 plus 2 plus x plus 2. So sorry, this is 4x. Okay, so this becomes 4x, this is 2x plus x, so you take x on this side and this becomes 2 plus 2 plus 2, that is 6. So this gives us the value of x as 6. So finally I can say I would need 6 number of trials to get 2 consecutive hits. Okay, so this is the expected number of tries needed to get 2 hits. Okay, so I hope you would be able to solve this problem now, and in the next video we will see a general case. If you want to get n consecutive hits. Okay, so what should be the expected number of tries, that we will see in the next video. Thanks a lot, see you guys in the next part. Hi everyone. So this problem is, what is the expected number of coin flips to get n consecutive hits? Okay, so we have raised the difficulty level here, and now you're interested in finding out what is the expected number of coin flips that is needed to get n consecutive heads. So let us discuss it case by case. So let's throw the coin and let's assume we end up getting a tail. Okay, so we can say x is going to be nothing but it's going to be equal to the probability of getting a tail into the number of throws that will be needed more. Okay, so to get n consecutive hits, so that will be x plus 1. Or it can happen on the first throw you get a tail, and on the next throw, on the first throw you get a head, on the next throw you will get a tail. So in this case we have wasted two of our throws, so this probability will be 1 by 4 into x plus 2. Okay, so that is the number of throws and this probability is 1 by 4. Or it can happen is we may get an head, get another head, and but on the third throw we get a tail. Okay, so that means we have wasted 3 flips, so that's 1 by 8 into x plus 3, and this will go on. Okay, and in the worst case what can happen, in the worst case it can happen that we got n minus 1 heads, but the nth was a tail. Okay, so this is n minus 1 heads followed by the next, or followed by the last throw that was a tail. Okay, so the probability of this event getting happened is going to be equal to 1 by 2 raised to the power n, and we have already wasted n throws. Okay, so n number of throws got wasted, so to expected number of flips will be x plus n. Okay, so all of these cases are the cases where we got a failure. Okay, and there will be one case where we got a success, in which all the throws, uh, all the n throws gave us heads. Okay, so in that case the sum that we will add, it will be 1 by 2 raised to the power n into n. Okay, so this is what we will add uh, to it. Okay, so this is the probability and this is what is the number of throws that we used here. Now let us try to simplify this equation. Okay, so I will take out the terms where I have x. Okay, so it becomes x followed by 1 by 2 plus 1 by 4 plus uh, 1 by 8 and so on up to 1 by 2 raised to the power n. Okay, so I take out these terms out, and also I have another series where I have 1 by 2 plus 2 by 4 plus 3 by 8 plus so on, and it becomes n by 2 raised to the power n till this term. Okay, and plus we have this term where it is n by 2 raised to the power n. So we also have this particular term here. So now if you see carefully, this part is nothing but this part is a GP. Okay, and if you see this part is nothing but it's a AGP. Okay, it's a arithmetic geometric progression, and you can use your knowledge of solving sum of a AGP to find out what is this particular sum, and that part is left as a homework for you. Okay, and you have to solve the sum of GP. This part is a homework for you, and you have to adjust these terms, and you have to come up with the final value of x. Okay, so the final value of x that you will get is, it should be equal to x is 2 raised to the power n plus 1 minus 2. Okay, so this is the general formula. And if I want to verify, let's say when n is 2, I want to get 2 consecutive heads, so this answer should come out to be 6. So let's verify. So it's 2 raised to the power 3 minus 2, so that's 8 minus 2, that's exactly 6. So that means this formula is correct, but it's your homework to solve this GP and AGP and to get this value of x. Okay, but I hope the way we have written this equation should be clear to you. Okay, so we have counted the cases where we got a failure, and we have counted the cases where we got the success. Okay, so that's it for this video, and see you guys in the next video. Okay, so the question says a fair coin flip experiment is carried out n times. So that means you are throwing a coin n times. What is the expected number of heads? Okay, so obviously you can guess the answer is going to be n by 2, but let's try to derive it mathematically. Okay, so let us say when you throw the first coin, or when you do the first experiment, let us assume your outcome is a random variable x1, and second time it's x2, the third time it is x3, and the nth time you do it is x of n. So we are interested in finding out e of x1 plus x2 plus x3 plus x of n. Okay, and using the rule of linearity of expectation, we can say this is nothing but e of x1 plus e of x2 plus e of xn. Okay, and now xn can take two values, so xn can be 1 and xn can be 0. Let's say it is 1 if it is a tail, and if it is a head, then it is 0. And we also know the expected value of getting a head. Okay, so e of x, it's going to be 0.5. So what you can do, you can just add 0.5. How many times? You have to add 0.5 n number of times. Okay, so this, if you do this, you will get n by 2 as the answer. Okay, so that says if you throw a coin n times, you can expect n by 2 heads, and similarly you can expect n by 2 number of tails. Okay, hi everyone. So in this video we will discuss what is a Bernoulli trial. So an experiment is called a Bernoulli trial if it has exactly two outcomes. Okay, and we are one of that outcome is desired by us. Okay, for example, when you throw a coin, a fair coin is thrown, so you get exactly two outcomes: either you get a head or you get a tail. Or for example, rolling a dice to get a 4. Okay, so in this case rolling a dice will have 6 outcomes, but if your goal is to get a 4, okay, then you can say, okay, getting a 4 is one outcome and getting a non 4 is another outcome. Okay, and similarly you have any event in which you have two outcomes such as success or failure, boy or girl, male or female, or selected or rejected. All those type of cases can be covered under Bernoulli trial. Okay, so we have a theorem that says if the probability of success of a Bernoulli trial is p, then the expected number of trials to get a success is 1 by p. Okay, for example, let's consider this example where we are interested in finding out what is the expected number of dice throws that we need to get a 4. So if we solve it using the expectation formula, we can say, let's assume the answer is x, and let's on the first throw we get a 4, so that probability is 1 by 6, and into the throw that was needed is 1, plus suppose we get a failure. So if we get a failure in the first throw, the probability of getting a failure is 5 by 6 into the number of throws that would be needed, so that would be equal to x plus 1. So if we just simplify this equation, so this becomes 6x, that's equal to 5x plus 5 plus 1. Okay, yes, so that's what it is going to be. So this becomes x equals to 6. So from here we get an answer as 6, but if you want to use a shortcut, so this is a shortcut formula. So if you want to get a success, so this formula is basically derived from this only. So it says if the probability of getting a success is p, then the expected number of trials to get a success is 1 by p. So in our case, let's say the probability of getting a 4 is 1 by 6. So the number of trials to get a 4 is going to be 1 by p. So that's equal to 1 upon 1 by 6, and you can say this is 6. So you can just do 1 by p and you can get the outcome. Okay, so there is another theorem which says if the probability of getting success in a Bernoulli trial is p, then the expected number of successes in n trials is n into p. So this basically says that if you want to if the probability of success, let's say x is a random variable, and if you do it n times, okay, so you have e of x1 plus e of x2 plus e of x3 up to e of x of n. So if the probability of getting success in a Bernoulli trial is p, then the expected number of successes in n trials is np. So if you just find this average out, it will turn out to be n into p. Okay, so yes, so the expected value of each is going to be p, and since you are combining these terms n times, so it will be n into p. Okay, so let us apply these two concepts in solving a problem. It says n students are asked to choose a number from 1 to 100. What is the expected number of students that would choose a single digit number? Now here you can define success as the probability of choosing a single digit number. So in a out of 100 numbers, you have only 9 numbers which are single digit. Okay, so if a single student does this experiment, then this probability of success is 9 by 100. Okay, and what is the expected number of students that would choose a single digit number? So according to the second theorem, we can say that since there are n students, so the expected number of students that would choose this particular number would be nothing but n into this value, n into p. Okay, so this is your result. Okay, so final answer is 9n by 100. Okay, so n students are asked to choose a number from 1 to 100, and what is the expected number of students that would choose a single digit number is 9n by 100. So that's it, and it's pretty easy. Okay, so we'll see some more examples in the coming videos, but that's all for this video. Hi everyone, so let's discuss a problem. It says candidates are appearing for an interview one after another. Probability of candidate getting selected is 0.16, and what is the expected number of candidates that you will need to an interview to select somebody? Okay, So pretty cool situation where you are taking an interview of some candidate instead of giving an interview. So you have to tell me how many interviews you will take in order to select someone. Okay, so let us assume our answer, expected number of interviews that we will take is X. So that is going to be broken down into two cases. So the first case is you get the first candidate and you select someone. So the probability of candidate getting selected is 0.16 into the number of interviews you took, that is 1, plus the first candidate that came in. Let's say you rejected that candidate and you said, okay, I will take X number of interviews more. So that's going to be 1 minus 0.16 into X plus 1. So this is what it's going to be. And if you just simplify this equation, it turns out to be X equals to 6.25. Okay, so this is the answer in this case. Okay, now such problems can also be solved using a Bernoulli trial. So as we know, what is a Bernoulli trial? So a Bernoulli trial is an experiment in which you have only two outcomes. Okay, so in a Bernoulli trial you have only two outcomes, that is success or a failure, yes or a no. So this problem can be treated as a case of Bernoulli trial where selecting a candidate is success and a candidate getting rejected is a failure. So if you want to calculate the expected number of interviews that you want to take, so that is given by 1 upon the probability of a candidate getting selected. So that's nothing but that's 1 upon 0.16 and that is equal to 6.25. So you can see we can solve it either using Bernoulli trial or we can solve it using the expectation formula. So both of them are correct and both of them give the same answer. So that's all. See you guys in the next video. Hi everyone. So let's discuss one very interesting problem statement. It's a category of problems that are called as coupon collector problems. So it says Uncle Chips brand always distributes a coupon in a packet of chips. Okay, so when you have this Uncle Chips pack, so you often get this Tazo or some distinct coupon from it, and it says the coupon collector wants to collect all n distinct coupons. So what is the expected number of chip packets one must buy so that you get all n distinct coupons? Okay, so in earlier times there used to be Pokemon coupons from these Uncle Chips and Cheetos packets. So you want to collect all the Pokemons, let's say. So what is the number of packets you will buy so that you uh, get all n distinct coupons? Okay, so here you have to think how you will approach this particular problem. Okay, so take 2 minutes to pause this video and try to think about the solution yourself. Okay, so now I'm going to discuss the solution for this particular problem. Okay, so let us denote a random variable xi that basically tells us, okay, that is the number of boxes it will take for the coupon collector to collect the ith new coupon. Okay, so let's say xi is a random variable that will denote the number of packets you will eat to get the ith new coupon. Okay, so ith new coupon basically means you already have I minus one distinct coupons. Okay, so maybe let's say the coupons are from in the range 1 to 100, and maybe you have already in the first packet you got 6, in the next packet maybe you got 8, or another you got 8 or 10. So when you eat 4 packets, maybe you already have 3 distinct coupons. Okay, so it's like if you want to get the fourth unique coupon, how many packets you will have to eat. So for that we can compute the expectation also. Okay, so expectation is the expected number of packets you will eat to get the ith new coupon. So that can be written as 1 upon p, where p is the probability of success, and here we can say the probability of success is nothing but the probability of getting a new coupon. Okay, so here our success is defined in terms of getting a new coupon. So if you have already collected, let's say if you want to collect the ith new coupon, so that means you already have I minus one distinct coupons. Okay, so what is the probability of getting a new coupon out of n coupons? So obviously you have n minus I minus one coupons which are new upon the total number of coupons. Okay, so this is n. So the expected number of packets that you will need to eat is going to be 1 upon p. So it's going to be n upon n minus I plus 1. Okay, so this is not the complete answer. This is the answer if you want to collect the ith new coupon. So what will happen in this case? So firstly, you can say the total number of coupons that you need to buy is, let's say total number of packets you need to buy is e of x, and that can be broken down into e of x1 plus x2 plus x3 up to x of n, and using rule of linearity of expectation, this can be written as e of x1 plus e of x2 plus e of x3 and plus e of x of n. Okay, so let us see what is the answer. So if I say x1, that means I want to try the I want to buy the first coupon, or I want to get the first coupon. So that is going to be n minus, the value of I is 1, so 1 minus 1 is 0. So it is n minus 0 upon n, plus if I put the value of I as 2, so n minus 1 upon n plus n minus 2 upon n. Sorry, this should be like this. So I have to actually put these values here. Okay, so if I put the value of I as 1, so I get e of x1 as 1. So you can see this is also logically true, because to buy the first to get the first unique coupon, you just need to buy only one packet. But if I put the value of I as 2 here, okay, so that means the number of packets I need to buy to get the second unique coupon. So it's going to be n divided by n minus 2 plus 1. So it's going to be uh, so it's going to be n minus uh, 2 plus 1, so that's n minus 1, and followed by n minus 2, followed by so on, and followed by n. Okay, so you will get something like this. So if you take n common, okay, if you take n common from here, so this can be written as 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 up to 1 by n. Okay, so this is going to be your final answer. Okay, so I hope this part is now clear, and here we used the Bernoulli trial formula to find out the expectation from the probability of success. So this is the probability of getting a success, and that's defined as the number of packets which are new upon the total number of packets. Okay, and I hope this problem is clear, and there is a related problem on Spoj that we can discuss in the next video. Hi everyone, so let's discuss this problem, 5 dice from Spoj. It says there is a boy who wants to play around his die. So there is a die with n sides, okay, and you have to tell me what is the expected number of throws so that each number is rolled at least once. Okay, so there is a dice that has n sides, and you have to tell me how many throws are needed so that at least every side is rolled at least once. Okay, so that's what you need to say. So now if you carefully analyze, this problem is exactly same as coupon collector problem. There is no difference at all, and you can use the formula that we had derived in the coupon collector problem to solve this problem. Okay, So we can say the expectation of getting all side is nothing but the expectation of getting each side. So we can use the rule of linearity of expectation, and that's comes out to be n into 1 plus 1 by 2 plus 1 by 3 plus up to 1 by n. Okay, so that's the formula to that you need to apply here and compute the result. So it's a very simple implementation problem, just a loop that's needed, and the only thing is you should know the coupon collector concept also. So a lot of people in the comments have also said they solved it using a coupon collector problem. So that's my code. So what I'm just doing is I'm taking a double variable answer, since precision is important in this problem, and I'm using a function set precision to set my precision up to 6 places. I think that's mentioned in the, okay, so it's not necessary, but it's the expected number must be accurate up to 2 decimal places. So it's fine if you give your answer up to 2 decimal places as well. So that's what you need to do. So very simple code, and I hope you will try out this problem by yourself and solve. So let us see what the problem is. So in the question you are given that you have an array A and it contains n positive integers. So there is an array which contains some positive integers, and you pick two integer numbers which are basically indices, right? So these are basically indices L and R, right, from the array, and these values are from 1 to n, right? So these are picked randomly, equiprobably and independently. So it means you are able to pick up all values of L and R, right? And finally you have to find out the number of unique elements in the segment of the array from index L to from index R, right? So what is the unique number of elements in that array? And it is also given if L is greater than R, then you will swap the values of L and R. So basically it is a symmetric case. Suppose L is here and R is here, and in the another case you pick, suppose R is here and L is here, then you are going to swap these values, right? You are not going to swap the integers in the array, you are just going to swap these indices, right? So R will come to this place and L will come to this place. So in both of these cases the answer is going to remain same because the segment is the same, right? So the segment is from R to L or from L to R. So if your answer from L to R is X, then for answer from R to L is also going to be X, right? So what we are going to do, we are going to compute for this case and we are going to double our answer, right? Because the total answer is 2x, right? The only exceptional case that we have to handle is when L equal to R, right? So in that case we cannot double our answer. In that case we have to count this case only once, right? So if L is here and R is here, so we cannot double it, right? So equal to wala case. So I'm going to find out my answer for L less than equal to R, and using this we will compute the answer for L greater than R also, right? इसके लिए भी कर लेंगे, right? So I think the problem statement needs to be elaborated more. So let us discuss one test case before moving forward. So in the first test case you are given there are two integers in the array and the array is like this. Let us numbers these integers are 1 and 2, and let us also give the indices also, right? So index of the array is from 1, so this index is 2. So we have to print the expected number of unique elements in the chosen segment. So we have to find out what all segments are possible. So segments can start from an index L and it can go to R, right? And we have to compute what is the expected value, expected unique elements in L to R. So let us say L is 1 and R is also 1. It means I am talking about this case. So expected unique elements, it is basically the probability of getting this value of L and R. So L can be chosen with the probability of half, R can be chosen with the probability of half, and what is the number of unique elements in this region? It is only 1. So this is nothing but 0.25. or let us say L is 1 and R is 2. So L is 1 and R is 2. So what is the value of choosing, what is the probability of choosing L as 1? So it is again half. Probability of choosing R as 2, half, into number of unique elements. So there are 2 unique elements in this region. So this answer is going to be 0.5. Again, let us say I pick L as this and R as this. So 2, 2, and I know the probability is half into unique elements, which is 1. So this is 0.25. Again, I can pick L as this and R as this. So this is going to be, L is going to be 2, R is going to be 1, and the probability is going to be half into number of unique elements, which are 2. So this is 0.5. So if you add up all these cases, then you will get your answer as 1.5. So which is the answer in the test case. So we have verified this test case. So this is how it is coming. So the brute force approach is to compute all values of L and R and then find the expectation value, right? But you know, the brute force is slow, and in this problem n is of the order 10 raised to the power 6. So your brute force solution, which is of the order O of n square, will not accept. This won't get accepted. So what I'm going to use, I'm going to use linear DP to solve this problem. So we will see how this is being done, right? So I will take up more examples to discuss this one, right? So we are going to solve this problem in O of n time with some pre-computation. So let us come back to here. Now let me take one example. We are talking about this problem, random query. And let me generate one test case, a custom test case. Let's say there is an array and it has these numbers 9, 6, 8, 5, 5, 2, 8, 9, 2 and 2. So I'm going to compute the answer for this test case and I'm going to show you how it is being done. So we are not going to use now brute force, we are going to use something different, right? So idea is to maintain a state answer I, right? So answer I will denote the number of unique elements, in all subarrays ending at index I. This is what I'm going to maintain, right? So answer of this position will denote the number of unique elements in all subarrays which are ending at this index, right? So these are the subarrays, right? Because I have to include this element. So since all subarrays ending at index I, so this I have to compute for all values of I and sum it, right? And I have to sum it because probability though same hogi L or R की, right? But the number of unique elements in all subarrays will vary, right? Because if some sub-subarray has redundant elements, then the repeating element will be counted only once. For example, this subarray. So this subarray has only unique 4 elements, right? So unique elements are 9, 6, 8 and 5. 5 is repeating, so we will count 5 only once, right? Another thing which I have to maintain, एक और चीज जो हमें मेंटेन करनी पड़ेगी, we have to maintain the last occurrence of the current element. this we will have to maintain, right? Because to make sure that the current element is not repeating, we will use this method of storing the last occurrence as well, right? So we will check if the current element is repeating or not. Now let us try to solve this using these two things, right? So let me have this array again: 9 6 8 5 5 2 8 9 and double 2. Let me add the indices. So indices are 1 2 3 4 5 6 7 8 9 and 10. So this has n equal to 10 elements. Now let us see what is the value of answer of I. So answer of 1 is going to be 1 because there is only one unique element. We are not talking about expectation value now, we are just counting the number of unique elements, right? So answer is just count of unique elements. It is not the expectation answer, right? Which we will find out later. Now let me talk about what is the value of answer of 2. Here I am going to denote, I am going to write answer here. So answer for this position is 1. So what is the answer for 6? So I know I can take this subarray and I can also take this subarray. So one subarray is 6 and another subarray is 9 6. So it has one element, it has two unique elements. So total number of unique elements is 3. So answer for this position is going to be 3. Now let me talk about this position 8. So one subarray is 8, another subarray is 6 8 and another subarray is 9 6 8, right? So you can clearly say the answer for this position is nothing but one element, two unique element and three unique elements, 6. So this position has 6 unique elements because 8 is not repeating. 8 is not, all these numbers are not repeating for now, right? So if you carefully analyze this thing, if you carefully analyze, you can say this can be written like this. This can be written as answer of this index I is nothing but answer of I minus 1 plus something. We will figure out what is this something, right? Answer of I minus 1. Why this thing? Because for all the subarrays which were ending at 6, I have just added 8 to it. I have just added 8 to it, right? So what I have added, so answer for this was 3 and I have added 3 to it, right? So answer of I minus 1 3 plus something. What is something? Something is 3 and here 3 is nothing but the index of 8, right? So this is the index of 8. But suppose 8 was coming before also, suppose 8 was coming earlier also, then we would have subtracted the last occurrence of 8 also. So this something is nothing but current index minus the last occurrence of 8. I will clarify this thing again. Let us first discuss the case of 5, right? So let me first discuss this case. So what about this thing? So for now I can say this is going to be nothing but 6 plus index of 5 if 5 is not repeating. So index of 5 is 4. So I know the answer is going to be 10. So this answer is going to be 10. Let us also verify how it is 10. So the first subarray is this, another subarray is 8 5, another subarray is 6 8 5, another subarray is 9 6 8 5. So it has one unique element, it has two unique elements, it has three unique elements, it has four unique elements. So you can see the answer is nothing but 10, which we have already computed. Now the tricky case arises when the number is repeating. Now this number is repeating, right? And I'm going to find out all sub arrays which are ending at this position. So I can say one of the sub array is going to be this one only, this only, right? So this sub array only, right? So for this sub array we have 5, and one could be this one. So for this we have 5. For this one we have again 1 5, 1 5 and 1 5. Now you can see that number of unique elements, these will remain same. These will be same because this has only one unique element, this has two unique elements, this has 4 unique elements, and this has 3 and this has 4 unique elements, right? So the only contribution to my answer is due to this, which is 1. So the answer for this position is going to be 11, right? So this position answer is going to be 11, right? And I can also say that answer of I is nothing but my previous answer of I minus 1 plus 1 plus 1. So how did I come to know that this value is 1? So this value is nothing but I minus previous occurrence of AI. This I have to compute, right? So I know what is the value of I here. I is 5 and previous occurrence of AI is nothing but 4. So 5 minus 4 is 1, right? So this we have done, right? Now let us try to compute for this position. So I know 2 is not repeating, so this is going to be 11 plus 6, 17, right? Because previous occurrence of AI is going to be 0. So this is the very important formula that I am going to use to compute. Now let us try to compute for this position 8, right? Now you know 8 is going to be repeated. 8 is repeating and last occurrence of 8 is here. 8 is occurring at third position, right? So let me try to figure out what all sub arrays are ending at 8. So what all sub arrays are ending at 8? So one sub array is 8 itself, one sub array is 2 8, another is 5 2 8, then another is 5 5 2 8, right? And we have more sub arrays, right? Then we have 8 5 5 2 8, then we have 6 8 5 5 2 8, and we have 9 6 8 5 5 2 8, right? So you know the contribution due to this 8 in these sub arrays is 0, where the 8 is repeating. Here the 8 is already there, so contribution of this 8 in the previous sub arrays is going to be 0. So effectively 8 has contributed only these many times. So 8 has contributed effectively 4 times to my previous answer. So what is the previous answer? So previous answer is, I know till 2 I know I have 17 unique elements. So it is 17 plus 4. So this answer for this position is going to be 21. Let me also verify using this. So you can say this subarray has 2 unique elements, this subarray has 1, this has 3, this has again 3, this has again 1 2 3, this has 1 2 3 4, and this has 5. So if I sum it, 5 4 9 12 15 18 20 and 21, so this is 21. So if I count all subarrays, I get only 21 unique elements. So again I am verifying how this 4 times is being coming. So 4 times kaise aa raha hai? So what I am going to do, I am subtract the index of this. What is the index of this? Index of this is 7, minus index of last occurrence. What is the index of this? 3. So it is nothing but 7 minus 3. So 4 times. So I can say this formula is justified now. This formula is justified. Similarly, if I compute for this position, so this will come out to be 21 plus 8 minus 1, which is 7. Right? So this will come out to be 28. And similarly, this position, it will come out to be 28 plus something, which is 31, and this will come out to be 32. Right? So this you can verify. Now let us try to compute what is the expectation value. Now we know the unique number of elements for each index ending at a position, right? So for every position we know, right? So what is the total number of unique elements in all the subarrays? It is going to be sum of all these elements. It is going to be sum of all these elements. So I am going to do summation answer of I. This I am going to do. Then after that, we need to compute. Let's say this value is nothing but sum. Let's say sum. This value is nothing but sum. Right? And let us now compute our final expectation value. Expectation we are going to compute. So expectation is going to be nothing but, now what is the probability of choosing L as this position and R as this position, right? So I know out of n elements I have to pick one position, so probability of choosing L is 1 by n, and for R it is also 1 by n. And my final answer is going to be nothing but 2 into sum divided by n square, right? Because if I do 1 by n square into number of unique elements from L to R into 1 by n square into number of unique elements L by R, so this can be written as summation answer I divided by n square. This can be written as, right? So I am writing it by sum divided by n square, right? So I have computed this sum already. This sum I have already computed. But the only case we are counting twice is this case, when L or R are equal, right? So we are counting this case twice. So when the value of L and R are equal, so we are counting this case as twice. So it means that all subarrays of size 1 have been counted twice. Now how we will handle it? So we know that this element has been counted twice. So there are n elements, so n elements have been counted twice. So what I am going to do, I am going to subtract. Right. First I am going to double my sum, and then I am going to subtract n. So this is the final formula for expectation, right? Because we are twice, because we have to consider LR and RL different, right? So symmetric case hai, so we have to twice the sum and we have to subtract n to make sure that we count this case only once. So we have to count this case only once. So this is the final formula for your expectation value. Twice of sum minus n upon n square. Right? So let us also try to verify this formula on our small example 1, 2. So I treat this case. So this is pretty easy. You can count what is the unique number of elements still here. It is 1. What is the unique number of elements still here? It is 2. Sorry, it is 3, right? So it is going to be 1 plus index of 2, right? 2 minus 0, right? So this is 3, and so final answer is going to be, so sum is going to be 4, and answer is going to be 2 into sum, which is 4, minus n, which is 2, divided by n square. What is the value of n square here? So n square is going to be 2 square, which is 4. So it is going to be 6 by 4 and it is 1.5, right? So you can see this formula is valid for the test case. Now I am going to write the code for this problem. I am going to write the code also, right? So let us see the coding part. So first input we have to take is n. Then I take input the value of n. Then let us take input the elements. So input the array, and I am storing from index 1 till n, right? Then I have two matrices. One is this last occurrence, one is my answer, right? So let me initialize them with 0, although we have done, but for safety, last occurrence is initialized to 0. Answer is also initialized to 0. Now answer of 0 is going to be 0, right? Because we are starting from index 1. And let me define another variable sum, which is 0. Now for every index I have to compute answer I. So answer of I is going to be answer of I minus 1 plus I minus last occurrence of array of I. And we have to update the last occurrence as well. So last occurrence of array of I is going to be I, right? And let us also compute sum. So sum is nothing but sum plus answer of I. So we have computed the sum, and we know final answer is going to be nothing but double final answer, and let's say this answer is 0 for now, and we are going to update our final answer as twice into sum, right? Divided by n square. So n into 1.0, and let's output our final answer. So here what I have done is to prevent the overflow, since the numbers are very large, since every number is of the order 10 raised to the power 6 and there are 10 power 6 numbers, so it is quite possible that the integer might overflow. So what, instead of writing 2 into sum minus n, what I did is I write 2 into sum minus n plus n, right? So this is same, so it is 2 into sum minus 2n plus n, so it is same as this thing. So this formula I have used here. So let us try some test case. So let first, in the first test case I have two elements, and these elements are 1, 2. So set precision is right, p should be small. So the answer is 1.5. Now let me submit it on Code Forces. Alright, so I'm not logged in, but this code will work, right? So this code will work. So thank you for watching. I hope you enjoyed this tutorial and learned a lot.